Hello, and welcome to another science lecture to help you rest. Tonight, we will talk about the different types of planets in the universe. We will explore the planets in our own solar system, and then travel to the worlds orbiting distant stars, learning about what makes each type unique. It is a very large topic, so we will go slowly and cover everything in detail. If you would like, you can subscribe to this channel for more lectures, or leave a comment below to let me know what subjects you might want to hear about in the future. For now, lie back and get comfortable. Close your eyes if you wish. There is nothing to see, only things to listen to. Allow your mind to settle as we begin our slow journey through the cosmos. Let the sound of this voice be a steady and calm presence. We will now transition to our topic. Part 1. Foundational concepts and the definition of a planet. To begin our discussion about the different types of planets, we must first have a very clear and solid understanding of what a planet actually is. The word is used commonly, but in science, having a precise definition is extremely important. The definition we use today is relatively new, formalized only in the year 2006 by a group of scientists called the International Astronomical Union. This organization is responsible for naming celestial objects and for making sure that astronomers all over the world are using the same language and the same definitions. Before this formal definition, the idea of what a planet was could be a little bit vague, which caused some confusion, especially when new objects were discovered in our own solar system. The International Astronomical Union established that for a celestial body to be called a planet, it must meet 3 specific conditions, or 3 criteria. It is not enough for it to meet 1 or even 2 of these criteria. It must meet all 3, without exception. This is a very strict rule. We will go through each of these 3 rules one by one in great detail to make sure we understand exactly what each one means. The first criterion is that the object must be in orbit around a star. In our case, that star is the Sun. So, for an object in our solar system to be a planet, it must travel around the Sun. An orbit is a path. It is a curved path that an object takes through space as it moves around another, much larger object. This path is not a choice. It is caused by the force of gravity. The Sun is incredibly massive, meaning it has a lot of matter packed into it. This large mass creates a very powerful gravitational pull. This pull reaches out across the entire solar system. A planet, like Earth, is also moving. It is moving forward in a straight line through space. However, the Sun's gravity is constantly pulling the planet towards it. The combination of the planet's forward motion and the Sun's inward pull creates a stable, curved path. This path is the orbit. The planet is always falling toward the Sun, but it is moving so fast sideways that it constantly misses. This state of continuously falling and missing is what we call an orbit. So the first rule is simple in concept. A planet cannot be an object that is just floating freely through the emptiness of space, unattached to a star. It must be gravitationally bound to a star, following a predictable path around it. This also means that an object orbiting another planet, like our moon orbits Earth, cannot be a planet. A moon orbits a planet, but a planet orbits a star. That is a critical distinction. The primary object that it circles must be a star. Let us think more about this first rule. The star does not have to be our Sun. There are billions of other stars in our galaxy, and we have discovered that many of them have planets orbiting them as well. These planets are called exoplanets, and we will talk much more about them later. But this first rule applies to them just the same. To be called a planet or an exoplanet, a world must be in a stable orbit around its parent star. It does not matter how big or small the star is, or what type of star it is. The rule is about the relationship between the two objects. One object, the planet, must be traveling around the other. Larger object, the star. The star is the anchor of the system. It is the central point around which everything else revolves. So, to summarize the first rule, a planet orbits a star. It is a simple but fundamental starting point for our definition. It separates planets from many other objects in the universe, such as moons, which orbit planets, and rogue planets, which we will discuss later, that do not orbit any star at all. They are wanderers in the dark between the stars. But for now, we focus on the standard definition. Rule 1. The celestial body must orbit a star. Now we move to the second criterion. This rule has to do with the shape of the object. The second rule states that the object must have sufficient mass to assume hydrostatic equilibrium. That phrase sounds very complicated, but the concept behind it is actually quite simple. It just means the object must be so massive that its own gravity has pulled it into a nearly round shape, like a sphere or a ball. Let us break that down. Mass is a measure of how much matter, how much stuff, is inside an object. The more mass an object has, the stronger its gravitational pull will be. Gravity pulls everything toward the object's center. Imagine a very young celestial body that is just forming. It is a lumpy, irregular collection of rock and dust and ice. As more and more material gathers together, the object's total mass increases. As the mass increases, its gravity gets stronger and stronger. At a certain point, the object becomes so massive that its gravity is strong enough to overcome the rigidness of its own material. The force of gravity begins to pull all the lumpy parts, all the high mountains and jagged edges, down toward the center. It tries to make the distance from the center to the surface the same in every direction. The most efficient shape for this to happen is a sphere. A sphere is a perfectly round, three-dimensional object. So, gravity acts like a giant, invisible hand, crushing the object and smoothing it out into a ball. This state of being, where the inward pull of gravity is balanced by the outward pressure of the material, is called hydrostatic equilibrium. Hydro means water or fluid, and static means not changing. The name suggests that the object is behaving a bit like a drop of water in space, which would naturally form a perfect sphere. A rocky planet is not a fluid, of course, but over very long periods of time, and under the force of immense gravity, the solid rock can slowly deform and flow until it settles into this balanced, round shape. So, the second rule is all about size and shape. An object needs to be big enough for its own gravity to make it round. This is what separates planets from smaller objects, like asteroids and comets. Most asteroids are not massive enough to become round. They are irregularly shaped, like potatoes or lumpy rocks. They are too small, and their gravity is too weak to pull them into a sphere. So, they keep their original, jagged shapes. A planet, on the other hand, must be a sphere, or at least very close to a sphere. Some planets might bulge slightly at their equator because they are spinning. but they are still fundamentally round. This is a key visual difference. When you see a picture of a planet, it is a ball. When you see a picture of an asteroid, it is a lump. This difference in shape is a direct consequence of the difference in mass, and it is the second major rule for being a planet. The object must be massive enough to be round. It must have achieved hydrostatic equilibrium. This leads us to the third and final criterion. This is the most recent and, for some, the most controversial part of the definition. It is also the reason that our understanding of the solar system changed in 2006. The third rule states that the object must have cleared the neighborhood around its orbit. This is a bit more abstract than the first two rules. Let us try to understand it clearly. Clearing the neighborhood is about being the boss of your own orbit. It means that the planet has become the gravitationally dominant object in its path around the star. As a planet travels along its orbital path, it interacts with all the other smaller bits of rock, ice, and debris that are also there. Over billions of years, a true planet will do one of three things to these smaller objects. It will either collide with them and absorb them, growing bigger in the process, or it will use its powerful gravity to fling them away into a different orbit or out of the solar system entirely, or it will capture them with its gravity and turn them into its own moons. The end result of all this is that the planet's orbit becomes relatively empty of other large objects. The planet has, in effect, cleaned up its own path. It is the king of its domain. There are no other bodies of a similar size or significance sharing its orbit, except for its own moons or some very small objects that it has trapped in special locations. So, this third rule is about gravitational dominance. A planet must not only orbit a star and be round, but it must also be massive enough to control its own orbital zone. It cannot be just one object among a crowd of many others in the same orbit. It must be the main object, the one that has dictated the fates of all the other smaller things that crossed its path. This is a very important distinction. Think about the asteroid belt, which is a region between Mars and Jupiter filled with millions of rocky objects. There is a dwarf planet in the asteroid belt called Ceres. Ceres orbits the Sun, so it meets the first criterion. Ceres is also massive enough that its own gravity has pulled it into a round shape, so it meets the second criterion. But Ceres has not cleared its neighborhood. It is just the largest of many, many objects all sharing a similar orbital region. It is surrounded by thousands of other asteroids. Therefore, according to the third rule, Ceres is not a planet. It is a dwarf planet. The same logic applies to other regions of the solar system, like the Kuiper Belt, beyond Neptune. This third rule, this idea of clearing the neighborhood, is what truly separates the 8 planets from the many other smaller worlds in our solar system. A planet is not just a passive object. It is an active shaper of its environment. It has to have enough gravitational influence to tidy up its own orbital space over the vast course of cosmic time. Now that we have established these 3 crucial rules, let's briefly look at the history of the word planet. Understanding where the word came from helps us appreciate how our scientific understanding has evolved. The word planet comes from the ancient Greek language. The Greek astronomers would watch the night sky very carefully. They noticed that against the backdrop of thousands of stars that seemed to stay in the same place relative to each other, there were a few points of light that moved. These stars did not stay fixed in their constellations. They seemed to wander across the sky over the course of nights and weeks. The Greeks called these moving lights planets, which means wanderers. To them, a planet was simply any bright object in the sky that moved against the fixed background of stars. Based on this ancient definition, the original list of planets was very different from what we know today. The wanderers that could be seen with the naked eye were Mercury, Venus, Mars, Jupiter, and Saturn. But the ancient observers also included the Sun and the Moon on their list of planets. This makes sense from their perspective. The Sun clearly moves across the sky every day, and the Moon moves against the background stars every night. So for a very long time, in the old Earth-centered model of the universe, there were 7 planets: the Sun, the Moon, and the 5 wandering stars. This understanding changed dramatically during the scientific revolution, particularly with the work of Nicholas Copernicus in the 16th century. Copernicus proposed a new model where the Sun, not the Earth, was at the center of the universe. In this sun-centered or heliocentric model, the Earth itself was reclassified. It was no longer the stationary center of everything. Instead, the Earth was understood to be just another planet, orbiting the Sun just like Mercury, Venus, Mars, Jupiter, and Saturn. The Sun was now the star at the center, so it was removed from the list of planets. The Moon was also reclassified. It was understood to orbit the Earth, not the Sun directly. So the Moon was no longer a planet, but a satellite of a planet. This was a massive shift in thinking. The definition of a planet changed from being a wanderer in the sky to being a world that orbits the Sun. This new definition held for hundreds of years. As telescopes became more powerful, new planets were discovered that fit this definition. Uranus was discovered in 1781. Neptune was discovered in 1846. And then, in 1930, a small, distant object was found, and it was named Pluto. For over 70 years, Pluto was widely known as the 9th planet in our solar system. School children learned its name, and it was included in all the models and diagrams of our cosmic neighborhood. This brings us to the famous and detailed case of Pluto, and why our understanding had to change again. The story of Pluto's reclassification is a perfect illustration of how the scientific process works. Science is not a collection of unchanging facts. It is a process of discovery, and as we learn new things, we must be willing to update our old ideas. For many decades after its discovery, Pluto seemed to be the final planet in our solar system. It was small, much smaller than any of the other 8 planets, and it had a very unusual orbit. Its orbit was highly elliptical or oval-shaped, and it was tilted at a strange angle compared to the other planets. For a portion of its long orbit, it even crossed inside the path of Neptune, but it did orbit the Sun, and it was assumed to be a planet. The problem began in the 1990s and the early 2000s. Astronomers started discovering many other objects in the outer reaches of the solar system, in a region beyond Neptune, called the Kuiper Belt. This is a vast, icy debris field, similar to the asteroid belt, but much, much larger. And in this Kuiper Belt, they started finding objects that were similar in size to Pluto. One object, discovered in 2005, was named Eris. When they measured Eris, they found that it was actually slightly more massive than Pluto. This created a huge problem for astronomers. If Pluto was a planet, then Eris, which was bigger than Pluto, must also be a planet. And if Eris was a planet, then what about all the other large round objects they were starting to find in the Kuiper Belt. Were there going to be 10 planets, or 12, or 50? The situation was becoming messy. The definition of a planet as simply an object orbiting the Sun was no longer good enough. A more precise definition was needed to bring clarity. This is what led to the meeting of the International Astronomical Union in 2006. They gathered to formally debate and vote on a new definition of a planet. It was this meeting that produced the 3 criteria we just discussed in detail. Let's apply those 3 rules to Pluto now and see why it was reclassified. First, does Pluto orbit the Sun? Yes, it does. It takes about 248 Earth years to complete one orbit, but it is most definitely gravitationally bound to our star. So, Pluto passes the first test. It meets criterion 1. Second, does Pluto have enough mass to be pulled into a nearly round shape? Yes, it does. Observations clearly show that Pluto is spherical. Its own gravity has been strong enough to overcome the strength of its icy and rocky material and form it into a ball. So, Pluto passes the second test as well. It meets criterion 2. Third, has Pluto cleared its neighborhood around its orbit? Here is where the problem lies. The answer is no. Pluto exists within the crowded region of the Kuiper Belt. Its orbit is full of other icy objects, asteroids, and comets. Pluto has not absorbed or ejected all of these other bodies. In fact, Pluto's own mass is only a tiny fraction of the total mass of all the other objects in its orbit. It is not the gravitational boss of its zone. Instead, it is better described as the largest member of a huge swarm of objects in the Kuiper Belt. It is like Ceres in the asteroid belt. It is a large and important object, but it is still just one object among many in a shared space. Because Pluto fails to meet this third criterion, the International Astronomical Union voted to reclassify it. Pluto is no longer considered a major planet. Instead, it was placed in a new category called a dwarf planet. A dwarf planet is an object that meets the first 2 criteria. It orbits the Sun and is round, but it does not meet the third. It has not cleared its orbital neighborhood. This new category was created to accommodate objects like Pluto, Ceres, Eris, and others that are planet-like in some ways, but not in others. So, the solar system officially went from having 9 planets back to having 8: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. This decision was upsetting to many members of the public who had grown up with Pluto as the 9th planet. But in science, decisions must be based on evidence and logical classification systems, not on sentiment or tradition. The reclassification of Pluto was a necessary step to create a consistent and scientifically sound definition of what a planet is. It reflected our new and more detailed knowledge of the outer solar system. We now understand that our solar system is not just 8 planets and a few asteroids. It is a complex place with different zones and different populations of objects. There are the inner, rocky planets, the outer gas and ice giants, the asteroid belt, and the vast Kuiper Belt with its many dwarf planets. To complete our foundational understanding, it is useful to clearly differentiate a planet from other types of celestial objects we have not focused on yet. We need to know what a planet is not. Let's start with the most fundamental comparison: a planet versus a star. The main difference between a planet and a star is how they produce energy. A star, like our Sun, is a gigantic ball of mostly hydrogen and helium gas. At the center of a star, the pressure and temperature are incredibly high. They are so extreme that they cause atoms of hydrogen to slam into each other and fuse together to form helium. This process is called nuclear fusion. Nuclear fusion releases an enormous amount of energy in the form of light and heat. This is why stars shine. They are their own power source. A planet, on the other hand, does not undergo nuclear fusion. Planets are much, much smaller and less massive than stars. Their cores are not hot enough or dense enough to ignite fusion. A planet does not generate its own light. The light we see from the planets in our night sky is just reflected sunlight. The planets are shining because the sun's light is bouncing off their surfaces or their atmospheres. So, the key difference is this: stars make their own light through fusion, while planets only reflect light from a star. Next, let's consider an object that lies somewhere in between a planet and a star. This object is called a brown dwarf. Brown dwarfs are often called failed stars. They are much more massive than even the largest planets, like Jupiter. A brown dwarf can be dozens of times more massive than Jupiter. However, they are not quite massive enough to start the process of nuclear fusion of hydrogen in their cores. The threshold to become a true star is about 80 times the mass of Jupiter. Brown dwarfs fall into the range between about 13 times the mass of Jupiter and 80 times the mass of Jupiter. Because they cannot sustain hydrogen fusion, they do not shine like a normal star. They are very dim and cool down over time. They might have a brief period of fusing a heavier type of hydrogen called deuterium, but this does not last long. So, a brown dwarf is an object more massive than a planet, but not massive enough to be a star. It occupies a fascinating gray area between these two major categories. Now, let's talk about moons. What is the difference between a planet and a moon? Some moons in our solar system are actually larger than the planet Mercury, so size is not the defining factor. The key difference, as we touched on earlier, is what the object orbits. By definition, a planet orbits a star. A moon, on the other hand, orbits a planet. A moon is a natural satellite of a planet. Earth has one moon. Mars has two very small moons. Jupiter and Saturn have dozens of moons each. These moons are gravitationally bound to their parent planet, and they travel with that planet as it orbits the star. So, if a large, round object is orbiting Jupiter, it is a moon. If that same object were to be kicked out of its orbit and instead began to orbit the Sun on its own, and if it cleared its new orbit, then it could potentially be reclassified as a planet. The context of its orbit is everything. Planet orbits a star. Moon orbits a planet. This is a simple but absolute rule in our system of classification. Finally, let's reiterate the difference between planets and the smallest members of the solar system, which are asteroids and comets, as we discussed when we talked about the second criterion for being a planet. The main difference here is mass and shape. Asteroids are relatively small, rocky or metallic objects that mostly orbit the Sun in the asteroid belt between Mars and Jupiter. Comets are also small objects, but they are made mostly of ice, rock, and dust. They often have very large elliptical orbits that take them from the outer solar system close to the Sun and then back out again. The vast majority of asteroids and comets are not massive enough to achieve hydrostatic equilibrium. Their gravity is too weak to pull them into a round shape. Therefore, they fail the second criterion for being a planet. They are irregularly shaped, like cosmic rubble left over from the formation of the solar system. The only exception is the very largest asteroid, Ceres, which is big enough to be round. And as we know, since Ceres meets the first two criteria, but not the third, it is classified as a dwarf planet, not a major planet, and not a simple asteroid. So, we have built a solid foundation. We have a clear, three-part definition from the International Astronomical Union. A planet must orbit a star. It must be massive enough for its gravity to make it round, and it must have cleared its neighborhood of other objects. We have seen how this definition evolved from the ancient idea of wandering stars to the modern, precise classification system we use today. We have examined the case of Pluto in great detail, understanding that its reclassification to a dwarf planet was a logical consequence of our improved knowledge of the solar system, and we have carefully distinguished planets from other celestial bodies, such as stars, brown dwarfs, moons, asteroids, and comets. Each of these objects has its own definition and its own place in the grand structure of the cosmos. With this clear and detailed understanding in place, we are now ready to begin our exploration of the different types of planets themselves, starting with the ones closest to us, the planets of our own solar system. This foundation will be essential as we encounter a wide variety of worlds, both familiar and strange, on our journey. The rules we have just laid out are the grammar of planetary science. They provide the structure we need to make sense of the diversity of worlds that exist in the universe. Without these rules, we would simply have a long list of objects. With these rules, we can begin to categorize them, compare them, and truly understand what makes each one special. The process of science is often a process of creating order out of chaos, and the definition of a planet is a prime example of that process in action. It provides a framework for our continued exploration of the cosmos. The 8 planets in our solar system are the definitive examples that meet all 3 criteria perfectly. They orbit the sun. They are all nearly spherical, and each one is, without a doubt, the gravitational master of its own orbital path. They are the benchmark against which all other potential planets are measured. Part 2. The terrestrial planets of our solar system. In this second part of our lecture, we will begin our detailed tour of the planets by focusing on the 4 planets closest to the Sun. These are the terrestrial planets. The word terrestrial comes from the Latin word for Earth, which is terra. So, a terrestrial planet is an Earth-like planet. This does not mean it is exactly like Earth, but that it shares certain fundamental characteristics with our own world. The 4 terrestrial planets in our solar system are Mercury, Venus, Earth, and Mars. They are also known as the inner planets because their orbits are all contained within the asteroid belt, that great band of rocky debris that separates the inner solar system from the outer solar system. The primary characteristic that defines a terrestrial planet is its composition. These planets are made mostly of rock and metal. They have solid surfaces upon which you could, in theory, stand. This is in stark contrast to the giant planets of the outer solar system, which are composed mainly of gas and ice, and do not have a solid surface in the same way. Terrestrial planets are much smaller and much denser than the gas giants. Their density comes from the heavy materials that make them up, like iron and silicate rock. They have a specific internal structure that is generally common to all of them. This structure consists of a central core, which is usually made of metal, primarily iron and nickel. Surrounding this core is a thick layer called the mantle, which is made of dense, hot rock, and on the very outside is a thin, solid shell called the crust. Because they are close to the Sun, the terrestrial planets formed in a region of the early solar system where it was very hot. The intense heat of the young Sun boiled away most of the lighter elements like hydrogen and helium, and also the volatile materials like water ice and methane ice. What was left behind were the heavier, more durable materials, the rock and metal that could survive the heat. These materials clumped together over millions of years to form the small, dense worlds we see today. The terrestrial planets also have fewer moons compared to the outer planets. Mercury and Venus have no moons at all. Earth has one large moon, and Mars has two very small, asteroid-like moons. This is very different from Jupiter and Saturn, which each have dozens and dozens of moons. So, to summarize, when we speak of terrestrial planets, we are speaking of the four inner worlds: Mercury, Venus, Earth, and Mars. They are small, rocky, dense worlds with solid surfaces and a core mantle crust structure. Now, let us begin our detailed examination of each of these worlds, one by one, starting with the planet closest to the Sun. Our first stop is the planet Mercury. Mercury is the smallest of the 8 planets in our solar system. It is only slightly larger than Earth's moon. It is also the planet that orbits closest to the Sun, making it a world of incredible extremes. Its proximity to the Sun has a profound effect on every aspect of the planet, from its orbit and rotation to its surface temperature and its very composition. Let us first consider Mercury's orbit and its rotation. Mercury travels around the Sun faster than any other planet. 1 year on Mercury, the time it takes to complete one full orbit, is only about 88 Earth days. While it moves through space very quickly, it spins on its axis very, very slowly. A day on Mercury is much longer than a day on Earth. It takes Mercury about 59 Earth days to rotate on its axis just once. This combination of a fast orbit and a slow rotation leads to a very strange situation. The length of a single solar day on Mercury, which is the time from one sunrise to the next, is actually about 176 Earth days long. This means that a single day on Mercury is longer than 2 of its years. For a very long time, astronomers thought that Mercury was tidally locked to the Sun, meaning that it would always show the same face to the Sun, just as our moon always shows the same face to the Earth. However, we now know this is not true. Instead, Mercury has what is called a 3-to-2 spin-orbit resonance. This means that for every 2 orbits it completes around the Sun, it rotates on its axis exactly 3 times. This stable, repeating pattern is the result of the Sun's immense gravitational pull on the slightly elongated shape of Mercury. This strange timing creates a very bizarre effect for an observer on the surface. The Sun would appear to rise in the east and then move slowly across the sky. But because of the planet's motion in its orbit, the Sun would seem to slow down, stop, move backward in the sky for a short time, and then resume its forward motion before eventually setting in the west, nearly 3 Earth months later. Next, let us discuss the physical characteristics of Mercury. Its diameter is about 4,879 kilometers, which is about 38% of Earth's diameter. Despite its small size, Mercury is surprisingly dense. It is the second densest planet in the solar system after Earth. This high density gives us a major clue about what is inside the planet. For a planet so small to be so dense, it must contain a very large amount of heavy material. This leads us to its internal structure. The most prominent feature of Mercury's interior is its massive metallic core. It is believed that Mercury's core is made mostly of iron and that it is enormous relative to the size of the planet. Current models suggest that the core has a radius of about 2,070 kilometers, which means the core makes up about 85% of the entire planet's radius. The core itself is likely composed of a solid inner part and a molten, liquid outer part, similar to Earth's core. The existence of a liquid outer core is supported by the fact that Mercury has a weak but global magnetic field. This magnetic field is only about 1% as strong as Earth's, but its presence suggests there is molten, conducting metal moving around inside the planet. Surrounding this giant core is a rocky mantle made of silicates, which is only about 500 to 700 kilometers thick. And on top of that is the crust, which is estimated to be about 100 to 300 kilometers thick. The question of why Mercury has such a disproportionately large core is a major topic of study. One leading theory is that early in its history, Mercury was a much larger planet, but it was struck by a giant object. This massive impact could have stripped away much of the planet's original mantle and crust, leaving behind the dense, iron-rich core with only a thin layer of rock on top. Now let us turn our attention to the surface of Mercury. The surface of Mercury looks very much like the surface of our own moon. It is a bleak, gray landscape that is absolutely covered in craters. These craters are the scars left behind by countless impacts from asteroids and comets over billions of years. Because Mercury has almost no atmosphere to burn up incoming objects and no weather to erode the surface, these craters have remained perfectly preserved for eons. The craters come in all sizes, from small, bowl-shaped depressions to vast, multi-ringed impact basins that are hundreds of kilometers across. The largest and most famous impact feature on Mercury is the Colossal Basin. This basin is a gigantic crater that is about 1,550 kilometers in diameter. That is large enough to fit the entire state of Texas inside it. The impact that created the Colossal Basin was so powerful that it sent seismic waves traveling all the way through the planet. On the exact opposite side of Mercury, from the Colossal Basin, there is a region of strange, jumbled, and hilly terrain. This area is sometimes called the weird terrain. It is believed that this landscape was created when the seismic waves from the Colossal impact converged on the other side of the planet, fracturing and disrupting the crust. Besides craters, another common feature on the surface of Mercury are long cliffs called scarps. These scarps can be hundreds of kilometers long and can reach up to 3 kilometers in height. They look like giant wrinkles on the planet's surface. These features are believed to have formed as Mercury cooled down after its formation. As the massive iron core cooled and solidified, it shrank. This shrinking of the interior caused the planet's solid crust to buckle and break, pushing up these long cliffs. The presence of these scarps all over the planet is strong evidence that Mercury has contracted in size by several kilometers in radius over its history. The surface also features large areas of smooth plains, especially within and between the large craters. These plains are thought to be volcanic in origin. They were formed long ago by lava flows that erupted from the planet's interior and flooded the low-lying areas. covering up the older, more heavily cratered terrain. Finally, we consider the atmosphere of Mercury, or more accurately, the lack of one. Mercury does not have a substantial atmosphere in the way that Earth or Venus does. The gravity of the small planet is too weak, and the heat from the nearby sun is too intense to hold on to a significant blanket of gas. Instead, Mercury has what is called a very thin exosphere. This is a fragile, tenuous layer of atoms that are blasted off the surface by the solar wind and by micrometeoroid impacts. This exosphere is made up of small amounts of oxygen, sodium, hydrogen, helium, and potassium. The pressure of this exosphere is so low that it is essentially a vacuum. The lack of a heat-trapping atmosphere leads to the most extreme temperature swings in the solar system. During the long day, when the surface is exposed to the direct and unfiltered radiation of the sun, the temperature can soar to over 425 degrees Celsius. That is hot enough to melt lead. But during the equally long night, with no atmosphere to hold in the heat, the temperature plummets to a frigid minus 180 degrees Celsius. So Mercury is simultaneously one of the hottest and one of the coldest planets. Interestingly, despite these scorching daytime temperatures, scientists have found evidence of water ice on Mercury. This ice exists in permanently shadowed craters near the planet's poles. The floors of these craters are tilted in such a way that they never receive any direct sunlight, allowing the ice to remain frozen in the deep cold of space. Our knowledge of Mercury has been greatly enhanced by two spacecraft. The Mariner 10 mission flew by the planet 3 times in the 1970s, and the Messenger spacecraft orbited the planet from 2011 to 2015, providing us with detailed maps and a wealth of data about this small, extreme world. Now we journey outwards from the Sun to the second planet, Venus. Venus is often called Earth's twin, or Earth's sister planet. This is because in some ways, it is remarkably similar to our own world. It is the closest planet to Earth in terms of distance, and its size, mass, and density are all very close to Earth's. However, despite these similarities, Venus is a profoundly different and hostile place. It is a planet that has evolved down a completely different path, resulting in a world that is anything but a twin to our own. Let us begin with the orbit and rotation of Venus. Venus orbits the Sun at an average distance of about 108 million kilometers. 1 year on Venus, the time it takes to complete one orbit, is about 225 Earth days. The most bizarre thing about Venus is its rotation. It has the slowest rotation of any planet in the solar system. It takes 243 Earth days for Venus to spin on its axis just once. This is longer than its year. So, a day on Venus is longer than a year on Venus. To make things even stranger, Venus rotates backward compared to most other planets. This is called retrograde rotation. On Earth, the Sun rises in the east and sets in the west. If you could stand on the surface of Venus, you would see the Sun rise in the west and set in the east. The reason for this slow, backward rotation is not fully understood. One leading theory is that it was caused by a massive collision with another large object early in the solar system's history. Another idea is that the very thick atmosphere of Venus has, over billions of years, created a tidal drag on the planet that has slowed its rotation and even reversed it. In terms of physical characteristics, Venus is very similar to Earth. Its diameter is about 12,000 104 kilometers, which is about 95% of Earth's diameter. Its mass is about 82% of Earth's mass. Because its size and mass are so similar, its overall density is also very close to that of Earth. This similarity suggests that Venus likely has a very similar internal structure to our own planet. Scientists believe that Venus has a metallic core, likely made of iron and nickel, with a radius of about 3,000 kilometers. This core is probably at least partially liquid. Surrounding the core is a rocky mantle, and on top of that is a silicate crust. However, unlike Earth, Venus does not appear to have active plate tectonics. There is no evidence of the large moving plates that shape Earth's surface. Also, Venus has a very, very weak magnetic field. This is surprising for a planet of its size, with a liquid core. The weakness of the magnetic field is probably due to its extremely slow rotation. The rapid spin of Earth helps to drive the dynamo effect in its liquid outer core that generates our strong magnetic field. The sluggish rotation of Venus means this dynamo does not operate in the same way. The surface of Venus is a place of intense heat and crushing pressure, but it is permanently hidden from our view by a thick, unbroken layer of clouds. We cannot see the surface with a normal telescope. Our knowledge of the Venusian surface comes from spacecraft that have used radar to pierce through the clouds and map the terrain below, most notably NASA's Magellan mission in the early 1990s. The radar maps revealed a world that is dominated by volcanism. The surface is covered in volcanoes, lava flows, and other volcanic features. There are thousands upon thousands of volcanoes on Venus. Most of them are shield volcanoes, similar to the ones found in Hawaii, but on a much grander scale. The largest volcano on Venus is called Mont Mons, which rises about 8 kilometers above the surrounding plains. The surface also has features that are unique to Venus. There are large, circular volcanic structures called coronae. These are thought to form when plumes of hot material from the mantle push up on the crust, causing it to bulge upwards and then collapse when the plume cools. There are also strange, flat-topped volcanic domes, often called pancake domes, which are thought to have formed from very thick, viscous lava. The surface of Venus appears to be geologically young, on average only about 300 to 600 million years old. This is much younger than the surfaces of Mercury or the Moon. There are also relatively few impact craters on Venus compared to other worlds. The craters that do exist are all large. This is because the planet's incredibly thick atmosphere burns up any small to medium-sized asteroids before they can reach the ground. The young age of the surface and the distribution of craters have led some scientists to propose a theory of catastrophic resurfacing. This idea suggests that about 500 million years ago, massive volcanic eruptions occurred all over the planet at once, covering the entire surface in a fresh layer of lava. The most extreme and defining feature of Venus is its atmosphere. The atmosphere of Venus is incredibly thick and dense. The pressure at the surface is about 92 times greater than the sea level pressure on Earth. This is equivalent to the pressure you would feel if you were 1 kilometer deep in Earth's ocean. The atmosphere is composed almost entirely of carbon dioxide, about 96.5%. The rest is mostly nitrogen, with trace amounts of other gases like sulfur dioxide. This carbon dioxide-rich atmosphere has led to a runaway greenhouse effect. The thick atmosphere lets sunlight in, which warms the surface of the planet. The surface then radiates this heat back out as infrared radiation. However, the carbon dioxide in the atmosphere is very good at trapping this outgoing infrared radiation, preventing it from escaping back into space. This process has turned Venus into a planetary oven. The average surface temperature on Venus is a staggering 465 degrees Celsius. This is hotter than the surface of Mercury. Even though Venus is farther from the Sun, the temperature is uniform across the entire planet. There is almost no difference in temperature between the equator and the poles, or between day and night. It is always scorching hot everywhere on Venus. The planet is also shrouded in a thick layer of clouds that extends from about 50 to 70 kilometers in altitude. These are not clouds of water vapor like on Earth. The clouds of Venus are made of droplets of sulfuric acid. These clouds are so thick that they reflect most of the sunlight that hits them, which is why Venus appears as such a bright white object in our sky. Above the clouds, the winds are incredibly fast, reaching speeds of over 360 kilometers per hour. These winds circle the planet in just 4 or 5 Earth days, a phenomenon known as superrotation. Despite the harsh conditions, several Soviet probes from the Venera and Vega missions successfully landed on the surface in the 1970s and 1980s. These landers only survived for a short time in the intense heat and pressure, but they were able to transmit back the only images we have ever taken from the surface of Venus. The pictures show a rocky, desolate, and dimly lit landscape under a yellow-orange sky. Venus has no moons. Now we move to the third planet from the Sun, our home, Earth. Earth is a unique and special place. It is the largest of the 4 terrestrial planets, and as of now, it is the only place in the entire universe where we know for certain that life exists. Its position in the solar system, its size, its composition, and its history have all combined to create a world with the perfect conditions to support a rich and diverse biosphere. Earth's orbit is nearly circular, at an average distance of about 150 million kilometers from the Sun. This distance is so important that it is used as a standard unit of measurement in astronomy, known as 1 astronomical unit. It takes Earth 365.25 days to complete 1 full orbit around the Sun, which we define as 1 year. The extra quarter of a day is why we have a leap year every 4 years. Earth rotates on its axis once every 24 hours, giving us our cycle of day and night. A crucial feature of Earth's rotation is its axial tilt. The Earth's axis, the imaginary line through the North and South poles, is not perfectly upright relative to its orbit. It is tilted by about 23.5 degrees. This tilt is the reason we have seasons. As Earth orbits the Sun, different parts of the planet receive the Sun's most direct rays. When the northern hemisphere is tilted towards the Sun, it experiences summer, while the southern hemisphere, tilted away, experiences winter. 6 months later, the situation is reversed. The internal structure of Earth is the most well-studied of any planet. At the center is a core, which is divided into 2 parts. There is a solid inner core, made mostly of iron and nickel, with a radius of about 1,220 kilometers. The temperature here is incredibly hot, estimated to be around 5,500 degrees Celsius, as hot as the surface of the Sun, but the pressure is so immense that the iron cannot melt. Surrounding this is a liquid outer core. also made of iron and nickel. This layer is about 2,260 kilometers thick. The constant churning and convection of the liquid metal in the outer core, combined with Earth's rotation, creates a powerful dynamo effect. This generates Earth's strong magnetic field, which extends far out into space and forms a protective bubble around our planet called the magnetosphere. This magnetic field deflects the harmful solar wind and cosmic rays, protecting the atmosphere and life on the surface. Above the core is the mantle, which is the thickest layer of the Earth, about 2,900 kilometers deep. The mantle is made of hot, dense silicate rock that flows like a very slow, thick liquid over millions of years. This slow movement is what drives plate tectonics. The outermost layer is the crust, which is very thin in comparison. The crust is where we live. There are two types of crust: the thin, dense oceanic crust that forms the ocean floors, and the thicker, less dense continental crust that makes up the land masses. The surface of Earth is dynamic and constantly changing. The most distinctive feature of our planet's surface is the presence of vast amounts of liquid water. About 71% of the Earth's surface is covered by oceans. This liquid water is essential for all known forms of life. The surface is also shaped by the process of plate tectonics. The Earth's crust is broken up into a number of large, rigid plates that are slowly moving over the mantle. Where these plates collide, they can push up enormous mountain ranges, like the Himalayas. Where they pull apart, they can create vast rift valleys. Where they grind past each other, they cause earthquakes. Volcanoes are also common at plate boundaries, where molten rock from the mantle, called magma, can rise to the surface over hundreds of millions of years. Plate tectonics has caused the continents to drift and rearrange themselves across the globe. Earth's atmosphere is another unique feature that is critical for life. It is composed of about 78% nitrogen, 21% oxygen, and about 1% argon, with small amounts of other gases, including carbon dioxide and water vapor. The oxygen in our atmosphere is a direct product of life itself, produced by plants and other photosynthetic organisms over billions of years. The atmosphere protects us from the sun's harmful ultraviolet radiation, thanks to a layer of ozone in the stratosphere. It also helps to regulate the planet's temperature through a moderate greenhouse effect, keeping the average surface temperature at a comfortable 15 degrees Celsius. The atmosphere is also the engine of our weather, with a constant circulation of air and the cycle of water, evaporation, and precipitation, creating clouds, rain, wind, and storms. Earth has one large natural satellite, the Moon. The Moon is unusually large relative to its parent planet. Its gravitational pull stabilizes Earth's axial tilt, which has helped to maintain a stable climate over long periods of time. The Moon's gravity also causes the ocean tides. Our final stop in the inner solar system is the fourth planet from the Sun, Mars. Mars has fascinated humans for centuries. It is often called the Red Planet because of its distinct reddish-orange color in the sky. It is a world of contrasts, a cold, desert planet that shows clear and abundant evidence that it was once a much warmer and wetter place, perhaps even capable of supporting life. Mars orbits the Sun at an average distance of about 228 million kilometers. A Martian year is significantly longer than an Earth year, lasting about 687 Earth days. However, a Martian day is remarkably similar to ours. Mars rotates on its axis once every 24.6 hours. This Martian day is called a sol. Like Earth, Mars has an axial tilt, about 25 degrees, which is very close to Earth's tilt. This means that Mars also experiences seasons, with winter, spring, summer, and autumn, although each season is about twice as long as on Earth. Mars is smaller than Earth and Venus. Its diameter is about 6,779 kilometers, roughly half the diameter of Earth. Its mass is only about 10% of Earth's mass. This smaller size means its gravity is weaker, only about 38% of Earth's gravity. The internal structure of Mars is thought to consist of a dense core made of iron, nickel, and a significant amount of sulfur. This core is likely solid, or at least not fully liquid, like Earth's. This would explain why Mars does not have a global magnetic field today, though there is evidence in its crust that it had one long ago. Surrounding the core is a rocky mantle and a crust that is thicker than Earth's and is not broken into tectonic plates. The surface of Mars is one of the most interesting and varied in the solar system. The most striking feature is its color. The rocks and soil on the surface are rich in iron oxide, which is essentially rust. This fine red dust covers most of the planet and is often whipped up into the atmosphere, giving the sky a pinkish hue. The Martian surface has a clear and dramatic dichotomy. The southern hemisphere is ancient, heavily cratered, and has a high elevation. It is known as the Southern Highlands. The northern hemisphere, in contrast, is much smoother, has a very low elevation, and has far fewer craters. These northern lowlands may have been the site of a vast ocean early in Mars's history. Mars is home to the largest volcanoes in the solar system. These are located in a huge volcanic plateau called the Tharsis region. The most famous of these is Olympus Mons. Olympus Mons is an enormous shield volcano. It is about 25 kilometers high, which is nearly 3 times the height of Mount Everest. Its base is about 600 kilometers in diameter, roughly the size of the state of Arizona. The volcanoes on Mars were able to grow so large because the crust does not move. On Earth, a volcano moves away from its source of magma over time, limiting its size. On Mars, a volcano could stay over a hotspot for billions of years, growing ever larger. Mars also boasts the largest canyon in the solar system, Valles Marineris. This is not a single canyon, but a vast system of interconnected canyons that stretches for over 4,000 kilometers along the Martian equator. It is up to 700 kilometers wide, and in places, it is 7 kilometers deep. This dwarfs Earth's Grand Canyon. Valles Marineris was likely formed by tectonic rifting as the crust was stretched and fractured by the formation of the nearby Tharsis Bulge. Perhaps the most compelling features on the Martian surface are those that point to a watery past. Orbiters and rovers have sent back images of features that look exactly like dried-up river valleys, deltas where rivers emptied into lakes, and ancient lakebeds. Rovers have analyzed rocks that could only have formed in the presence of liquid water. Today, the water on Mars exists almost entirely as ice. There are large polar ice caps at both the North and South Poles. These caps are made of a combination of water ice and frozen carbon dioxide, or dry ice. They grow and shrink dramatically with the changing seasons. There is also a great deal of water ice frozen in the ground beneath the surface, especially at higher latitudes. The atmosphere of Mars today is very thin, less than 1% the density of Earth's atmosphere. It is made up of about 95% carbon dioxide with small amounts of nitrogen and argon. Because the atmosphere is so thin, it cannot retain much heat. The temperature on Mars is very cold. The average temperature is about minus 63 degrees Celsius. Even on a summer day at the equator, the temperature might reach 20 degrees Celsius, but at night it would plummet to minus 73 degrees Celsius. The thin atmosphere also means that liquid water cannot remain stable on the surface. The pressure is so low that any liquid water would quickly boil away. Despite its thinness, the atmosphere can produce weather, including clouds of water ice and massive dust storms. These dust storms can sometimes grow so large that they cover the entire planet for weeks at a time. Mars has two very small moons, Phobos and Deimos. They are not round like our moon. They are small, lumpy, and irregularly shaped. They are most likely asteroids that were captured by Mars's gravity long ago. The relentless exploration of Mars by a fleet of orbiters, landers, and rovers continues to reveal the secrets of this fascinating world, searching for more clues about its past climate and whether life ever arose on the red planet. Part 3. The gas giant planets of our solar system. We now leave the inner, rocky worlds behind. We have crossed the great dividing line in our solar system, a vast region of space known as the asteroid belt. This belt is filled with millions of rocky bodies, the leftover rubble from the formation of the planets. Beyond this belt, we enter a completely different realm, the realm of the giants. This is the outer solar system, and it is dominated by planets of a scale and nature that are almost beyond our everyday comprehension. The first two of these giants that we will encounter are the gas giants, Jupiter and Saturn. They are called gas giants because that is precisely what they are, enormous globes made almost entirely of gas, with no solid surface to stand on. The differences between the terrestrial planets we just discussed and the gas giants are profound and absolute. The terrestrial planets are small, dense, and rocky. The gas giants are immense, not very dense, and gaseous. The sheer scale is the first thing to understand. Jupiter, the larger of the two, is so big that all the other planets in the solar system, including Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, could fit inside it with room to spare. Their composition is also fundamentally different. While the inner planets are made of rock and metal, the gas giants are composed primarily of the two lightest and most abundant elements in the universe, hydrogen and helium. This is the same material that stars are made of. In many ways, Jupiter and Saturn are more like small, failed stars than they are like large versions of Earth. Another critical difference is the concept of a surface. On a terrestrial planet like Earth or Mars, there is a clear boundary where the atmosphere ends and the solid ground begins. You can land on it. On a gas giant, there is no such thing. There is no solid surface. As you descend into a gas giant, the gaseous atmosphere simply gets thicker and denser and hotter. The pressure increases to unimaginable levels. The gas gradually transitions into a strange, exotic liquid state, without ever passing through a distinct surface. To speak of landing on Jupiter or Saturn is a meaningless concept. You would simply sink deeper and deeper into the planet, being crushed by the immense pressure and vaporized by the incredible heat until you became part of the planet itself. These worlds are vast oceans of gas and liquid, all the way down to a small, mysterious core at their very center. They also have extensive systems of moons, numbering in the dozens, and are all adorned with beautiful systems of rings. With these fundamental differences in mind, let us begin our detailed exploration of the king of the planets, the magnificent and mighty Jupiter. Jupiter is the fifth planet from the Sun, and it is, by a very large margin, the largest and most massive planet in our solar system. Its size is truly staggering. Its diameter is about 143,000 kilometers. To put that into perspective, you could line up 11 Earths side by side to span the diameter of Jupiter. Its volume is so great that more than 1,300 planets the size of Earth could fit inside it. Jupiter's mass is more than twice the mass of all the other planets, all the moons, all the asteroids, and all the comets in the solar system combined. It is a true giant, a dominant presence in our cosmic neighborhood. Its immense mass gives it a powerful gravitational pull that has shaped the solar system in profound ways. Jupiter's gravity acts like a giant cosmic gatekeeper. It has likely prevented many comets and asteroids from the outer solar system from traveling inwards and striking the Earth. Its gravity has also herded the asteroids into the stable band of the asteroid belt and is responsible for creating gaps within that belt. Jupiter orbits the Sun at a distance of about 778 million kilometers, which is more than 5 times the distance of Earth from the Sun. Because it is so far away, it takes a long time for Jupiter to complete one journey around the Sun. A year on Jupiter is very long, lasting for almost 12 Earth years. While its year is long, its day is incredibly short. Despite being the largest planet, Jupiter is also the fastest spinning planet in the solar system. It completes one full rotation on its axis in less than 10 hours. This rapid rotation has a noticeable effect on the planet's shape. The quick spinning motion causes the planet to bulge out at its equator and flatten slightly at its poles. This means Jupiter is not a perfect sphere. It is what scientists call an oblate spheroid. This bulging is a direct consequence of the immense centrifugal force generated by its high-speed rotation, which counteracts gravity more at the equator than at the poles. Now, let us delve into the composition and the internal structure of this colossal world. As we mentioned, Jupiter is made almost entirely of hydrogen and helium. Its overall composition is about 90% hydrogen and about 10% helium by volume, with trace amounts of other substances like methane, ammonia, and water. This composition is very similar to that of the Sun. If Jupiter had been about 80 times more massive when it formed, the pressure and temperature in its core would have become high enough to ignite nuclear fusion, and it would have become a star. As it is, Jupiter is a gas giant planet, not a star. It does generate some of its own heat, however. Jupiter radiates about twice as much energy into space as it receives from the distant Sun. This internal heat is a remnant from its formation 4.5 billion years ago, as well as heat generated by the planet's slow, ongoing gravitational contraction. Because we cannot directly see inside Jupiter, its internal structure is determined by scientific models that are based on its size, mass, density, rotation rate, and the data gathered by spacecraft. Most recently, NASA's Juno mission, which is currently orbiting the planet. These models paint a picture of a planet with several distinct layers. defined by the changing state of hydrogen under immense pressure. The outermost layer is the part we can see, the atmosphere. This layer is what we think of when we picture Jupiter, with its colorful clouds. As you descend through this atmosphere, the pressure and temperature begin to rise steadily. The hydrogen gas becomes denser and denser. At a depth of about 1,000 kilometers below the cloud tops, the pressure becomes so great that the hydrogen gas no longer behaves like a normal gas. It reaches a point where it transitions into a state of liquid molecular hydrogen. In this state, the hydrogen atoms are still paired up as they are in a normal gas, but they are packed together as densely as a liquid. This vast ocean of liquid molecular hydrogen continues to extend deeper into the planet. As we continue our imaginary journey downwards, the pressure and temperature keep increasing to truly mind-boggling levels. At a depth of about 21,000 kilometers, we reach the most exotic layer of Jupiter's interior. Here, the pressure is millions of times greater than the atmospheric pressure on Earth. Under this crushing weight, the liquid molecular hydrogen undergoes another radical transformation. The intense pressure squeezes the hydrogen atoms so hard that their electrons are stripped away from their protons. These electrons are no longer bound to any single atom, but are free to move around throughout the substance. When a material has electrons that can move freely, it can conduct electricity, just like a metal. So, in this deep layer of Jupiter, the hydrogen behaves like a liquid metal. This strange, electrically conductive state of hydrogen is called a metallic hydrogen. This layer of metallic hydrogen is enormous, making up the bulk of Jupiter's interior. The constant, swirling motion within this vast ocean of liquid metallic hydrogen, combined with the planet's rapid rotation, creates a powerful dynamo effect. This dynamo generates Jupiter's magnetic field, which is the strongest of any planet in the solar system. It is nearly 20,000 times more powerful than Earth's magnetic field. This magnetic field creates a gigantic magnetosphere around Jupiter that stretches out for millions of kilometers, trapping charged particles and creating intense radiation belts that are dangerous for any spacecraft that flies through them. Finally, at the very center of the planet lies the core. The exact nature of Jupiter's core is still a subject of intense scientific research and debate. For a long time, it was thought that Jupiter had a small, dense core of rock and ice, perhaps about 10 to 15 times the mass of the Earth, compressed to an incredible density by the weight of the planet above it. However, recent data from the Juno spacecraft has suggested a more complicated picture. It seems that Jupiter's core may not be a distinct, solid ball. Instead, it might be what is called a fuzzy or dilute core. This means that the heavy elements, the rock and ice, are not neatly separated at the center. They may be partially dissolved and mixed into the metallic hydrogen layer above, creating a large, gradually denser region at the planet's center rather than a sharp boundary. This is a new and exciting idea that is changing our understanding of how giant planets form and evolve. So, to summarize the journey inside Jupiter, we start with a gaseous atmosphere, which transitions into a deep ocean of liquid molecular hydrogen, which then becomes an even deeper ocean of liquid metallic hydrogen. And at the very center, there is a core of heavy elements that is likely fuzzy and mixed with the hydrogen above it. Now let us return to the part of Jupiter we can actually see, its vibrant and dynamic atmosphere. The atmosphere of Jupiter is one of the most visually spectacular and chaotic places in the solar system. The colorful, swirling patterns we see are the tops of cloud layers. The atmosphere is organized into distinct parallel bands that circle the entire planet. The lighter colored bands are called zones, and the darker colored bands are called belts. These bands are not just painted on, they are powerful weather systems. The zones are regions of rising gas. As the gas rises, it cools, and ammonia ice crystals form, creating high, thick clouds that are white or yellow in color. The belts, on the other hand, are regions of falling gas. As the gas sinks, it warms up, and the ammonia clouds evaporate, allowing us to see deeper into the atmosphere to darker colored cloud layers made of other chemicals, like ammonium hydrosulfide, which are thought to produce the reddish-brown colors. The boundary between these zones and belts are home to extremely powerful jet streams. The winds on Jupiter are ferocious, regularly reaching speeds of over 360 kilometers per hour. In some places, they can be much faster. These winds blow in opposite directions in adjacent bands, with the eastward flowing winds in the zones and the westward flowing winds in the belts. This creates immense shear and turbulence at the boundaries, leading to the formation of countless swirls, eddies, and vortices. The entire atmosphere is a churning, chaotic mess of storms. The most famous storm on Jupiter, and indeed in the entire solar system, is the Great Red Spot. The Great Red Spot is a gigantic, persistent storm that has been observed for at least 150 years, and possibly for more than 300 years. It is an anticyclone, which means it is a high-pressure system that rotates in a counterclockwise direction in Jupiter's southern hemisphere. Its size is immense. For centuries, it was large enough to contain 2 or 3 Earths. In recent decades, it has been observed to be shrinking, and it is now only about 1.3 times the diameter of Earth. But it is still the largest and most powerful storm known to exist. The top of its clouds are higher and colder than the surrounding clouds of the zone it resides in. The reason for its distinct reddish color is still not fully understood. It may be due to complex organic molecules or compounds of sulfur or phosphorus that are created when chemicals from deep within the atmosphere are dredged up by the storm and exposed to ultraviolet sunlight. The Great Red Spot is not the only storm on Jupiter. The planet is covered with many other smaller storms. There are numerous white ovals, which are smaller anticyclones, and brown ovals, which are cyclones. These storms can last for years or decades, and they often interact with each other, sometimes merging to form larger storms. Jupiter's atmosphere is a natural laboratory for studying fluid dynamics on a planetary scale, a world of perpetual, violent weather. Now, we move on to the second gas giant, the 6th planet from the Sun, Saturn. Saturn is arguably the most beautiful and iconic planet in our solar system, thanks to its breathtaking system of rings. It is the second largest planet after Jupiter, and it shares many similarities with its larger sibling. But it also has its own unique and fascinating characteristics. Saturn orbits the Sun at a distance of about 1.4 billion kilometers, which is nearly twice as far from the Sun as Jupiter is. This great distance means that its year is very long. Saturn takes more than 29 Earth years to complete a single orbit around the Sun. Like Jupiter, it spins very rapidly on its axis, completing a rotation in about 10.7 hours. This fast rotation also causes Saturn to be an oblate spheroid, bulging at its equator and flattened at its poles. In fact, Saturn is the most flattened planet in the solar system because of its fast spin and its low density. The most famous physical characteristic of Saturn is its incredibly low density. Saturn is a huge planet with a diameter of about 120,000 kilometers, which is only slightly smaller than Jupiter's. However, its mass is only about 95 times the mass of the Earth, which is less than a third of Jupiter's mass. This means that Saturn is a very puffy planet for its size. Its average density is less than the density of water. This leads to the famous, though impractical statement, that if you could find a bathtub large enough, Saturn would float. This is simply a way of illustrating just how low its density is. It is the only planet in our solar system that is less dense than water. This low density tells us that, like Jupiter, it must be composed almost entirely of the lightest elements, hydrogen and helium. The internal structure of Saturn is thought to be very similar to Jupiter's, but with some important differences due to its lower mass and therefore lower internal pressure. It is believed to have a core of rock and ice at its center, with a mass estimated to be somewhere between 10 and 20 times that of Earth. Surrounding this core is a layer of liquid metallic hydrogen, just like in Jupiter. However, because the pressure inside Saturn is not as high as it is inside Jupiter, the layer of metallic hydrogen is thought to be significantly smaller. Above this is a very deep layer of liquid molecular hydrogen, which then gradually transitions into the gaseous atmosphere. One unique feature of Saturn's interior is believed to be the source of its extra heat. Like Jupiter, Saturn radiates more energy than it receives from the Sun, but Saturn is smaller and less massive, so the leftover heat from its formation should have dissipated more than Jupiter's has. Scientists believe that the extra heat is generated by a process called helium rain. Inside Saturn, it is cool enough, and the pressure is right for helium to condense out of the hydrogen-helium mixture. This helium forms droplets that are denser than the surrounding hydrogen, and so they rain down towards the planet's core. As these helium droplets fall, the friction they create with the hydrogen generates heat. This process of helium raining down from the upper layers also explains why Saturn's upper atmosphere is slightly depleted of helium compared to Jupiter's. This is a fascinating process, unique to Saturn among the planets in our solar system. The atmosphere of Saturn is also similar to Jupiter's in its basic structure, but it has a more subdued appearance. It has the same pattern of alternating bands, the zones, and the belts, and it has extremely fast winds. In fact, the winds on Saturn are even faster than on Jupiter, reaching speeds of up to 1,800 kilometers per hour near the equator. These are some of the fastest winds in the solar system. The reason Saturn's appearance is more muted and its colors are paler than Jupiter's is because Saturn is colder. Being farther from the Sun, its upper atmosphere is colder, which allows a thicker layer of ammonia, haze, to form at a higher altitude. This haze layer acts like a veil, obscuring our view of the more colorful cloud layers that lie deeper down. While Saturn does not have a persistent giant storm like Jupiter's Great Red Spot, it does experience enormous storms of its own, about once every 30 years, which is roughly once per Saturnian year. A massive storm, known as the Great White Spot, erupts in its northern hemisphere. These storms can grow to be thousands of kilometers across and are powerful enough to encircle the entire planet before they eventually fade away. And now, we come to the defining feature of Saturn, its magnificent ring system. While other giant planets, including Jupiter, also have rings, they are faint and barely visible. Saturn's rings are broad, bright, and extraordinarily complex, making them one of the true wonders of the solar system. From Earth, they appear as a solid, continuous disk. But this is an illusion. The rings are not solid. They are made up of countless individual particles of ice and a small amount of rock. The size of these particles varies enormously, from tiny specks of dust as small as a grain of sand, to chunks of ice the size of a car, to a few boulders as large as a house or a small mountain. All of these billions of particles are in orbit around Saturn, forming a flat, thin disk. The rings are incredibly thin when compared to their width. The main ring system extends out to about 282,000 kilometers from the planet, but its average thickness is only about 10 meters. This makes the rings proportionally thinner than a sheet of paper. If you were to make a scale model of the rings that was 1 kilometer across, the rings themselves would be thinner than a human hair. This extreme thinness is why the rings seem to disappear when we view them edge-on from Earth, which happens every 15 years or so as Saturn moves along its orbit. The rings are not a single, uniform structure. They are divided into several main groups, which are named with letters in the order of their discovery. The brightest and widest rings, easily visible from Earth with a small telescope, are the A and B rings. These two rings are separated by a prominent gap called the Cassini division, which is about 4,800 kilometers wide. The Cassini division looks empty from a distance, but it is actually filled with ring material, just much less densely than the A and B rings. Inside the B ring is the fainter C ring, and beyond the A ring is the very faint F ring. There are other, even fainter rings, like the D and E rings, that are much harder to see. The intricate structure of the rings, with their thousands of individual ringlets and gaps, is maintained by the gravitational influence of Saturn's many moons. Small moons that orbit within or near the rings are called shepherd moons. Their gravity acts like a sheepdog herding a flock of sheep. They help to keep the ring particles confined to narrow, well-defined bands. For example, the narrow F ring is held in place by two small shepherd moons, Prometheus and Pandora, one orbiting just inside the ring and one just outside. The gravitational pull of the larger, more distant moons also creates resonances with the ring particles, clearing out gaps in the rings. Much like Jupiter's gravity clears out gaps in the asteroid belt, the Cassini division, for instance, is created by the gravitational pull of the moon Mimas. Any particle in that region would orbit Saturn exactly twice for every one orbit of Mimas, and the repeated gravitational tugs from Mimas would eventually pull it out of that orbit. The origin of Saturn's rings is still not definitively known, but there are two main theories. One theory is that the rings are the remains of a moon, or perhaps a large comet or asteroid that strayed too close to Saturn. Inside a certain distance from a planet, known as the Roche limit, the tidal forces of the planet's gravity are stronger than the gravitational force holding the moon together. The moon would have been torn apart into countless small pieces, which then spread out into a disk around the planet. A second theory suggests that the rings are not from a destroyed body, but are leftover material from the original nebula from which Saturn formed. In this scenario, the material in the rings was never able to clump together to form a large moon because it was too close to Saturn, and the tidal forces prevented it from coalescing. Recent data from the Cassini spacecraft, which orbited Saturn for 13 years, suggests that the rings are relatively young, perhaps only 100 million to 200 million years old. This would favor the theory that they formed from a destroyed moon, as it is unlikely that leftover material from the solar system's formation would have survived for this long. Regardless of their origin, the rings of Saturn are a dynamic and ever-changing system, a celestial spectacle of unparalleled beauty that perfectly encapsulates the grandeur of the outer solar system. Part 4. The Ice Giant Planets and Dwarf Planets. Continuing our journey outward from the Sun, we move beyond the orbit of Saturn and into the deep, cold, and dark outer reaches of the solar system. Here, we encounter the final two major planets, Uranus and Neptune. These two worlds form a distinct class of planet, separate from both the terrestrial planets and the gas giants. They are known as the ice giants. This name can be a little bit confusing, so it is important to understand what astronomers mean by ice in this context. When an astronomer talks about ices, they are not just talking about frozen water. They are referring to a group of chemical compounds that are more volatile than rock and metal, but less volatile than hydrogen and helium. These compounds include water, of course, but also ammonia and methane. In the cold environment of the outer solar system, these substances would have existed as solid ice particles in the early solar nebula. Uranus and Neptune are primarily composed of these ices, which is what sets them apart from the gas giants, Jupiter and Saturn, which are made almost entirely of hydrogen and helium. The ice giants are smaller than the gas giants, but they are still much, much larger than the terrestrial planets. Uranus and Neptune are very similar to each other in size and composition, almost like a pair of twins. They are both about 4 times the diameter of Earth. While they are smaller than Jupiter and Saturn, they are still very massive. Uranus has a mass of about 14.5 times the mass of Earth, and Neptune is even more massive, at about 17 times the mass of Earth. An interesting fact is that even though Neptune is slightly smaller than Uranus in diameter, it is significantly denser and more massive. The internal structure of the ice giants is different from that of the gas giants. At the very center, they are thought to have a relatively small, rocky core, perhaps about the mass of the Earth. But unlike Jupiter and Saturn, the bulk of an ice giant's interior is not a vast ocean of metallic hydrogen. Instead, surrounding the core is a very large and extensive mantle. This mantle is not made of rock, like Earth's mantle. It is a hot, dense, fluid mixture of the ices we talked about: water, methane, and ammonia. The temperatures and pressures in this mantle are so high that it is sometimes called a water ammonia ocean. It is not a liquid in the ordinary sense, but a supercritical fluid, a strange state of matter that is both hot and electrically conductive. This moving conductive fluid is what generates the unique magnetic fields of Uranus and Neptune. Above this massive, icy mantle is the atmosphere, which is made mostly of hydrogen and helium, like the gas giants. But it also contains a significant amount of methane gas, which plays a crucial role in their appearance. Now, with this general understanding of what an ice giant is, let us look at each of these distant mysterious worlds in more detail, starting with the seventh planet from the Sun, Uranus. Uranus is a planet that is barely visible to the naked eye from Earth, and even then, only under very dark, clear skies. It was the first planet to be discovered using a telescope. It was found by the astronomer William Herschel in the year 1781. For a long time, Uranus remained a faint and mysterious point of light. Our first and only close-up look at the planet came in 1986, when the Voyager 2 spacecraft flew by on its grand tour of the outer solar system. Uranus orbits the Sun at an immense distance, about 2.9 billion kilometers away. This is about 20 times the distance of Earth from the Sun. As you would expect, its journey around the Sun is incredibly long. 1 year on Uranus lasts for 84 Earth years. For an entire human lifetime, Uranus would not even complete a single orbit. The most defining and bizarre characteristic of Uranus is its extreme axial tilt. As we discussed before, Earth is tilted on its axis by about 23.5 degrees, which gives us our seasons. Jupiter is tilted by only about 3 degrees, but Uranus is tilted by an astonishing 98 degrees. This means that the planet is essentially lying on its side as it orbits the Sun. Its axis of rotation is pointed almost directly at the Sun for parts of its orbit. This extreme tilt leads to the most extreme seasons in the solar system. For a quarter of its long 84-year orbit, one pole of Uranus is pointed directly at the Sun, while the other pole is plunged into total darkness. This means that each pole experiences a continuous 21-year-long summer day, followed by a 21-year-long winter night. During the spring and autumn equinoxes, when the planet is side on to the Sun, it experiences a more normal cycle of day and night as it rotates. Uranus rotates on its axis relatively quickly, with one day lasting about 17 hours and 14 minutes. The reason for this incredible tilt is not known for sure, but the leading theory is that early in its history, Uranus was struck by a massive Earth-sized object. This catastrophic collision would have been powerful enough to knock the entire planet over onto its side. Let's discuss the internal structure and composition of Uranus. As we mentioned, it fits the model of an ice giant. It is thought to have a small, rocky core at its center. Above this is the vast, hot, and dense mantle, made of water, ammonia, and methane ices. This icy mantle makes up about 80% of the planet's total mass, and on the outside is the atmosphere. The atmosphere of Uranus is composed primarily of hydrogen, about 83%, and helium, about 15%. The remaining 2% is mostly methane. This methane is what gives Uranus its distinctive color. Methane gas is very good at absorbing red light from the Sun, while it reflects blue and green light. This is why the planet has a pale, blue-green, or cyan appearance. The atmosphere of Uranus appears surprisingly bland and featureless compared to the stormy atmospheres of Jupiter and Saturn. When Voyager 2 flew by, it saw a calm, almost uniform bluish haze with very few visible clouds or bands. It was sometimes called the most boring planet. This lack of features is partly due to the fact that Uranus has a very low internal heat. Unlike Jupiter, Saturn, and Neptune, Uranus does not radiate much more heat than it receives from the Sun. It has a very cold interior. This lack of internal heat means there is less energy to drive strong convection and create the kind of violent weather we see on the other giant planets. However, since the Voyager flyby, More powerful telescopes, like the Hubble Space Telescope, have observed Uranus and have seen more activity. As the planet moved towards its equinox, when the sun was shining more directly on the equatorial regions, astronomers have seen the formation of bright clouds and even large, dark storms, similar to those on Neptune. So, the atmosphere of Uranus is more dynamic than it first appeared, but it is still the calmest of the four giant planets. Uranus also has a very strange and unusual magnetic field. The magnetic field is not generated in the planet's core, but in the moving, conductive fluid of its icy mantle. What is truly strange is that the magnetic field is not centered on the planet's geometric center. It is offset from the center by about 1/3 of the planet's radius. Furthermore, the magnetic axis is tilted by a huge 60 degrees relative to the planet's axis of rotation. This means that the magnetic north and south poles are nowhere near the geographic north and south poles. The magnetic field wobbles and tumbles around as the planet rotates. This odd configuration is likely a result of the complex fluid motions within the icy mantle, but it is still not fully understood. Like all the giant planets, Uranus has a system of rings and a large family of moons. The rings of Uranus are very different from the bright, icy rings of Saturn. They are very dark and very narrow. The particles that make up the rings are not coated in bright eyes. Instead, they are composed of a very dark material, possibly rock and radiation processed organic compounds, making them as dark as charcoal. This is why they are so difficult to see from Earth. There are 13 known rings in total. The brightest of these is called the Epsilon ring. Uranus also has 27 known moons. These moons are not named after figures from Greek or Roman mythology like the other planets' moons. Instead, they are named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. These are all relatively small, icy worlds. The moon Miranda is particularly interesting, with a bizarre and jumbled surface that looks like it has been shattered and put back together again, possibly as a result of a major impact in its past. Now we travel even further out to the 8th and final planet in our solar system, Neptune. Neptune is the most distant of the major planets, orbiting the Sun at a frigid and dark distance of about 4.5 billion kilometers. This is 30 times farther from the Sun than Earth is. Because it is so far away, sunlight is very faint at Neptune, about 900 times dimmer than it is at Earth. Neptune receives so little heat from the Sun that it is one of the coldest places in the solar system. Neptune's great distance from the Sun also means its orbit is incredibly long. It takes Neptune almost 165 Earth years to complete a single trip around the Sun. This means that since its discovery in the year 1846, Neptune has only completed one full orbit. It completed its first full orbit since discovery in the year 2011. Neptune's day is a little shorter than Uranus's, with the planet completing one rotation in about 16 hours. Its axial tilt is about 28 degrees, which is quite similar to Earth's and Mars's, so it experiences seasons. But each season lasts for more than 40 years. Neptune was discovered in a very different way from all the other planets. It was discovered through mathematics before it was ever seen in a telescope. After the discovery of Uranus, astronomers noticed that its orbit was not quite what their calculations predicted. It seemed to be getting pulled and tugged by the gravity of some unknown object farther out in the solar system. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated the position of this hypothetical eighth planet. Le Verrier sent his predictions to the Berlin Observatory, and on the very first night of searching, the astronomer Johann Galle pointed his telescope to the predicted spot in the sky and found Neptune, very close to where the calculations said it should be. It was a stunning triumph for science and for Newton's law of universal gravitation. Like Uranus, our only close-up view of Neptune came from the Voyager 2 spacecraft, which flew past in 1989. Neptune and Uranus are very similar in size, but as we said, Neptune is more massive and denser. This suggests that Neptune has a slightly larger, rocky core than Uranus, or that its mantle is more compressed. Its internal structure is otherwise thought to be very similar to Uranus's, with a small rocky core, a large, hot mantle of water, ammonia and methane ices, and an outer atmosphere of hydrogen and helium. However, there is one major difference. Unlike Uranus, Neptune has a strong internal heat source. It radiates more than 2.5 times the energy it receives from the sun. This internal heat has a dramatic effect on its atmosphere. The atmosphere of Neptune is one of the most dynamic and stormy places in the solar system. The internal heat drives powerful convection currents, creating a much more active and visually interesting atmosphere than that of Uranus. Neptune is known for having the fastest winds in the solar system, with speeds reaching an incredible 2,100 kilometers per hour. These winds blow in a westward direction, opposite to the planet's rotation. When Voyager 2 flew by, its most prominent feature was a huge, dark, oval-shaped storm called the Great Dark Spot. This storm was an anticyclone, similar in nature to Jupiter's Great Red Spot, and was about the size of the Earth. It was a giant hole in the upper cloud deck, allowing us to see into the deeper, darker layers of the atmosphere. However, when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot was gone. It had disappeared completely. Since then, other dark spots have appeared and vanished in Neptune's atmosphere, suggesting that its storms are much less permanent than Jupiter's. The atmosphere also features bright, white, high-altitude clouds made of frozen methane crystals. These clouds are often called scooters because they zip around the planet at very high speeds. The vibrant, deep blue color of Neptune is also a result of methane in its atmosphere. Like Uranus, the methane absorbs red light, but Neptune is a much richer, more vivid shade of blue. The reason for this more intense color is not fully understood. It may be that there is another, unknown chemical compound in its atmosphere that contributes to the blue color, or it could be that the haze on Neptune is thinner than on Uranus, allowing us to see the blue color more clearly. Like Uranus, Neptune has a strange, offset, and tilted magnetic field, which is also generated in its icy mantle. Neptune has a faint and dark ring system, similar to the rings of Uranus. There are 5 main rings, and they are clumpy and uneven. Some parts of the rings are much denser and brighter than others, forming bright arcs. These arcs are thought to be held in place by the gravity of a small nearby moon. Neptune has 14 known moons. The vast majority of them are very small. However, one of its moons, Triton, is very large and very unusual. Triton is the 7th largest moon in the solar system, larger than the dwarf planet Pluto. The most remarkable thing about Triton is its orbit. It orbits Neptune in a retrograde direction, meaning it orbits in the opposite direction to the planet's rotation. This is very unusual for a large moon. A retrograde orbit is a strong indication that Triton was not formed around Neptune. Instead, it is believed to be a captured object from the Kuiper Belt, a vast region of icy bodies that lies beyond Neptune's orbit. It was a world that formed independently and then strayed too close to Neptune, where it was captured by the planet's powerful gravity. Triton is a geologically active world. Voyager 2 saw giant plumes of nitrogen gas and dark dust erupting from its surface, a form of icy volcanism or cryovolcanism. Its surface is very young and is covered in frozen nitrogen, water ice, and carbon dioxide ice, making it one of the coldest objects in the solar system. With a surface temperature of about minus 235 degrees Celsius, our tour of the major planets is now complete. But our exploration of the solar system is not. Beyond the orbit of Neptune lies a vast and mysterious region of space known as the Kuiper Belt. This is a donut-shaped ring of icy objects, a third zone of the solar system, after the inner rocky planets and the outer giant planets. It is similar to the asteroid belt, but it is far larger, about 20 times as wide and 20 to 200 times as massive. The objects in the Kuiper Belt are remnants from the early solar system, icy bodies that never came together to form a planet. This is the home of the object that led to the redefinition of what a planet is. This is the domain of the dwarf planets. As we discussed in the first part of our lecture, a dwarf planet is a celestial body that meets the first two criteria for being a planet, but not the third. It must orbit the sun. It must be massive enough for its own gravity to pull it into a round or nearly round shape. But it has not cleared its orbital neighborhood of other objects. The Kuiper Belt is full of such objects. There are likely hundreds of dwarf planets waiting to be discovered in this distant region. For now, the International Astronomical Union officially recognizes 5 dwarf planets: Ceres, Pluto, Haumea, Makemake, and Eris. The first dwarf planet on the list, Ceres, is the only one not located in the Kuiper Belt. As we mentioned before, Ceres is located in the asteroid belt between Mars and Jupiter. It is the largest object in the asteroid belt, containing about a third of the belt's total mass. Ceres is about 940 kilometers in diameter, and it is round. It is a unique object, a sort of transition between the rocky asteroids and the icy bodies of the outer solar system. It is believed to have a rocky core and a mantle that is rich in water ice. In fact, Ceres may contain more fresh water than the entire Earth. Data from the Dawn spacecraft, which orbited Ceres, revealed a dark, cratered surface with mysterious bright spots. These bright spots are now known to be deposits of salt, likely left behind after salty water from beneath the surface sublimated into space. This suggests that Ceres may have a briny liquid layer under its icy crust, making it a target of interest in the search for habitable environments. Now, we move to the most famous dwarf planet, Pluto. Pluto was discovered in 1930 and was considered the 9th planet for over 75 years. It resides in the Kuiper Belt, and its orbit is highly unusual. It is very elliptical or oval-shaped, and it is tilted by 17 degrees relative to the main plane of the solar system. For part of its 248-year orbit, Pluto actually comes closer to the Sun than Neptune does. Pluto is a small world with a diameter of about 2,377 kilometers, which is smaller than Earth's moon. Our understanding of Pluto was completely revolutionized in 2015 when the New Horizons spacecraft flew by, providing our first detailed images of this distant world. The images revealed a surprisingly complex and geologically active planet. The surface of Pluto is incredibly varied. There are vast plains of frozen nitrogen, most notably a large heart-shaped feature, unofficially named Tombaugh Regio. This plain is smooth and almost entirely free of craters, suggesting it is geologically very young, possibly resurfaced by ongoing geological processes. There are also towering mountains made of water ice that rise several kilometers high. There are ancient, heavily cratered dark regions, and there are strange textures on the surface that look like the skin of a snake. Pluto also has a thin atmosphere, mostly made of nitrogen with some methane and carbon monoxide, which freezes and snows back onto the surface as the dwarf planet moves away from the Sun in its long orbit. Pluto has a system of 5 moons. The largest of these is Charon, which is so large relative to Pluto, about half its diameter, that the two are often considered a binary system. The other 4 moons are small and irregularly shaped. The other 3 officially recognized dwarf planets are also located in the Kuiper Belt and are less well known. Haumea is a very strange object. It is not spherical. It is elongated, shaped like a flattened American football. This shape is due to its extremely rapid rotation. It spins on its axis once every 4 hours. It is also known to have its own ring system and 2 small moons. Makemake is the second brightest object in the Kuiper Belt after Pluto. It is slightly smaller than Pluto and appears to have a reddish color, likely due to the presence of tholins, complex organic molecules formed by sunlight acting on methane. It has 1 known moon. And finally, there is Eris. Eris is the object whose discovery triggered the debate that led to the reclassification of Pluto. It is located far beyond Pluto, in a region of the Kuiper Belt known as the scattered disk. Eris is almost the same size as Pluto, but it is about 27% more massive, meaning it is much denser and contains more rock. For a time, it was thought to be larger than Pluto, which earned it the informal title of the 10th planet. Eris has a highly elliptical orbit and takes 557 years to circle the Sun. It has 1 small moon named Dysnomia. The discovery of Eris and other large objects in the Kuiper Belt showed us that Pluto was not a lonely outpost at the edge of the solar system. Instead, it is the largest member of a vast population of similar icy worlds. This new understanding of the solar system's structure, with its 3 distinct zones, the inner rocky planets, the outer giant planets, and the distant icy bodies of the Kuiper Belt, necessitated a new and more precise classification system. The creation of the dwarf planet category was a logical and necessary step to accommodate this new knowledge, providing a home for these fascinating worlds that are large enough to be round, but not quite dominant enough to be called full-fledged planets. They are a kingdom of their own, ruling over the cold, dark frontiers of our solar system. Part 5. Exoplanets and the methods of their detection. We have now completed our detailed tour of the planets and dwarf planets within our own solar system. We have traveled from the scorched, cratered surface of Mercury all the way out to the cold, distant realm of the Kuiper Belt. For a very long time, these were the only planets we knew. Our solar system was the only example of a planetary system in the entire universe. But for centuries, thinkers and scientists have wondered if this could be true. They looked up at the countless stars in the night sky and asked a simple, profound question. Are there planets orbiting those other stars? Is our sun unique in having a family of worlds, or are planets a common and natural consequence of the birth of a star? For most of human history, this question was purely a matter of speculation. The stars are incredibly far away. Even the closest star to our sun, Proxima Centauri, is over 40 trillion kilometers away. Trying to see a small, dim planet orbiting a distant, bright star is an immense technological challenge. It has been compared to trying to spot a tiny firefly buzzing around a giant, brilliant searchlight from thousands of kilometers away. The light from the star is so overwhelmingly bright that it completely drowns out the faint, reflected light from any orbiting planet. For this reason, for a very long time, we simply could not see them. But in the last few decades, all of that has changed. Through the development of incredibly sensitive instruments and clever new techniques, astronomers have finally been able to answer that ancient question. And the answer is a resounding yes. Planets orbiting other stars are not rare. They are incredibly common. It now seems that most, if not all, stars have planets. These planets that orbit stars other than our sun are called extrasolar planets, or more commonly, exoplanets. The discovery of exoplanets has started a revolution in astronomy, transforming our understanding of planetary systems and our place in the cosmos. We are no longer limited to the 8 examples in our own backyard. We now have thousands of examples of other solar systems, each with its own unique arrangement of worlds. The very first exoplanets to be definitively confirmed were discovered in the year 1992, and surprisingly, they were not found orbiting a normal star like our sun. They were found orbiting a pulsar, which is the tiny, super dense, spinning remnant of a massive star that has exploded. This was a very strange and unexpected discovery. The first exoplanet to be found orbiting a sun-like star was discovered a few years later, in 1995. This planet was named 50 Pegasi b. Its discovery marked the true beginning of the age of exoplanet exploration. Since then, the number of known exoplanets has exploded. As of today, we have confirmed the existence of over 5,000 exoplanets, and there are thousands more potential candidates waiting for confirmation. The vast majority of these have been discovered by a single, incredibly successful mission, NASA's Kepler Space Telescope. Since we cannot usually see these exoplanets directly, how do we find them? How can we be sure that a planet is there when we cannot take a picture of it? Astronomers have developed several ingenious, indirect methods for detecting the presence of these distant worlds. These methods do not rely on seeing the planet itself, but on observing the subtle effects that a planet has on its parent star. We are going to spend this part of our lecture exploring these detection methods in great detail, one by one. Understanding how we find exoplanets is just as important as knowing what types of exoplanets exist. The two main methods which have been responsible for the vast majority of all exoplanet discoveries are the transit method and the radial velocity method. We will also discuss some other techniques like direct imaging and gravitational microlensing. Let us begin with the most successful technique of all, the transit method. This method is responsible for more than 3/4 of all known exoplanets, largely thanks to the Kepler Space Telescope, which was specifically designed to use this technique. The concept behind the transit method is very simple and easy to understand. Imagine you are looking at a distant, bright light bulb. If a small moth flies directly between you and the light bulb, it will block a tiny fraction of the light, and the bulb will appear to dim slightly for a moment. The transit method works in exactly the same way. An exoplanet is the moth, and its star is the light bulb. For the transit method to work, the planetary system we are observing must be aligned in just the right way. The orbit of the exoplanet must be oriented edge-on from our point of view here on Earth. This means that, from our perspective, the planet must pass directly in front of its star as it goes around in its orbit. When the planet passes in front of its star, this event is called a transit. During a transit, the planet blocks a small amount of the star's light. From our vantage point, the star will appear to get just a little bit dimmer for a short period of time. This dimming is incredibly small. For a Jupiter-sized planet passing in front of a sun-like star, the star's brightness would dip by only about 1%. For an Earth-sized planet, the dip in brightness is 100 times smaller, only about 1/100th of 1%. This is a minuscule change, far too small for the human eye to see, but it can be measured by highly sensitive telescopes. So, the transit method involves staring at a star, or many thousands of stars at once, for a very long time, and measuring their brightness with extreme precision. The telescope takes a measurement of the star's brightness over and over again, maybe every few minutes, for months or even years. The data collected is a long list of the brightness measurements over time. This data is then plotted on a graph, with time on the horizontal axis and the brightness of the star on the vertical axis. This graph is called a light curve. For most of the time, the light curve will just be a flat, straight line, indicating that the star's brightness is constant. But if a planet transits the star, we will see a small, characteristic dip in the light curve. The brightness will go down, stay down for a few hours while the planet is crossing the face of the star, and then go back up to its normal level once the planet has passed. A single dip in brightness is not enough to confirm the existence of a planet. It could be caused by other things, like a spot on the star's surface or a problem with the telescope's instrument. To be confident that we have found a planet, we need to see the dip happen repeatedly, and it must happen at regular, predictable intervals. This is because a planet in a stable orbit will transit its star once every orbit. If we see a dip in the star's light that repeats every, for example, 10 days, then we can be very confident that we are seeing a planet with a 10-day orbital period. Seeing at least 3 of these periodic dips is the standard for a planet to be considered a candidate. The transit method can tell us a surprising amount of information about the planet, even though we cannot see it directly. First, as we just mentioned, the time between transits tells us the planet's orbital period. This is the length of the planet's year. Once we know the orbital period, and we know the mass of the star, we can use Kepler's laws of planetary motion to calculate the size of the planet's orbit, or its average distance from the star. This is a very important piece of information. Second, the amount of light that is blocked during the transit tells us the size of the planet. A larger planet will block more of the star's light, creating a deeper dip in the light curve. A smaller planet will block less light, creating a shallower dip. The percentage of light that is blocked is directly related to the ratio of the planet's area to the star's area. Since we can usually estimate the size of the star based on its type and brightness, we can then calculate the size, or the radius, of the exoplanet. This is how we can tell if we have found a giant planet like Jupiter or a small, rocky planet like Earth. The transit method is particularly good at finding large planets that orbit close to their stars. Because these planets produce deeper and more frequent transits, making them easier to detect. The transit method is incredibly powerful, but it has one major limitation. It only works for planetary systems that are perfectly aligned with our line of sight. The planet's orbit has to be edge-on. If the planet's orbit is tilted, even by a small amount, it will not pass in front of its star from our perspective. It will pass above or below the star, and no transit will occur. We will never see a dip in the star's light. The probability of this alignment being just right is actually very small. For a planet in an Earth-like orbit around a Sun-like star, the chance of its orbit being aligned correctly is only about 0.5%. This means that for every 200 solar systems like our own, we would only be able to detect the Earth in one of them using the transit method. For planets that orbit much closer to their star, the probability is higher, but still, the transit method can only detect a small fraction of all the planets that are actually out there. This is why missions like Kepler had to stare at a huge number of stars, over 150,000 of them, in order to find thousands of transiting planets. Despite this limitation, the transit method has been the most productive way of finding exoplanets and has given us a huge amount of data about the sizes and orbits of planets in our galaxy. Now, let's move on to the second major detection technique, the radial velocity method. This method is also known as the Doppler wobble method, and it was the first technique to successfully find a planet around a sun-like star. Before the transit method became so dominant, the radial velocity method was responsible for most of the early exoplanet discoveries. The concept behind this method is a little less intuitive than the transit method, but it is based on a very solid physical principle. When a planet orbits a star, we often think of the planet as moving around a stationary star, but that is not entirely accurate. Gravity is a two-way street. The star pulls on the planet, keeping it in orbit, but the planet also pulls on the star with its own gravity. Because the star is so much more massive than the planet's pull is much weaker. It doesn't cause the star to move around in a big circle. Instead, it causes the star to wobble. The planet and the star are actually orbiting a common center of mass. The center of mass is the balance point of the system. Because the star is so heavy, this center of mass is very close to the center of the star, often inside the star itself, but it is not exactly at the center. So, as the planet makes its large orbit, the star makes a very small corresponding orbit, or a wobble, around this common center of mass. The radial velocity method does not detect this tiny side-to-side wobble on the scusae. That motion is far too small to see directly. Instead, it detects the star's motion towards and away from us. As the star wobbles, part of its motion will be directed towards Earth, and part of its motion will be directed away from Earth. And we can detect this motion using something called the Doppler effect. The Doppler effect is a familiar concept. It is the change in the frequency of a wave in relation to an observer who is moving relative to the wave source. The classic example is the sound of an ambulance siren. As the ambulance approaches you, the sound waves are compressed, and the pitch of the siren sounds higher. As the ambulance moves away from you, the sound waves are stretched out, and the pitch of the siren sounds lower. The same thing happens with light waves. If a star is moving towards us, the light waves it emits are compressed. This shifts the light to a higher frequency, which means it becomes bluer. This is called a blue shift. If a star is moving away from us, the light waves are stretched out. This shifts the light to a lower frequency, which means it becomes redder. This is called a red shift. This change in color is far too subtle to be seen with our eyes, but it can be measured with an instrument called a spectrograph. A spectrograph takes the light from a star and splits it into its component colors, creating a spectrum, like a rainbow. This spectrum is not perfectly smooth. It has dark lines in it at very specific colors, or wavelengths. These dark lines are called absorption lines, and they are created by different chemical elements in the star's atmosphere absorbing light at specific frequencies. These lines act like a barcode for the star. They have a very precise, known position in the spectrum. If the star is moving, the Doppler effect will shift the position of this entire barcode of absorption lines. When the star is wobbling towards us, all the lines will be shifted slightly towards the blue end of the spectrum. When the star is wobbling away from us, all the lines will be shifted slightly towards the red end of the spectrum. By carefully measuring the position of these lines over time, astronomers can track the star's wobble. They can see the lines shifting back and forth, from blue to red, and back to blue again, in a periodic cycle. The speed of this motion towards or away from us is called the radial velocity. So, by measuring the star's radial velocity, we are measuring its wobble. And if we see a regular, periodic wobble, we can infer the presence of an unseen orbiting planet that is causing the star to move. The radial velocity method can also tell us important information about the planet. The time it takes for the star to complete one full wobble cycle, from maximum blue shift to maximum red shift and back again, is equal to the planet's orbital period. Just like with the transit method, this allows us to calculate the size of the planet's orbit, the amplitude of the wobble, which is the maximum speed the star reaches as it moves towards or away from us, tells us about the planet's mass. A more massive planet will exert a stronger gravitational pull on the star, causing it to wobble more vigorously with a higher speed. A less massive planet will cause a smaller, slower wobble. So, a bigger wobble means a more massive planet. The radial velocity method gives us a lower limit on the planet's mass, often called its minimum mass. This is because the strength of the observed wobble also depends on the tilt of the planet's orbit. We see the biggest wobble if the system is edge-on. If the orbit is tilted, we only see a component of the full wobble, so the true mass might be higher. The radial velocity method has its own strengths and weaknesses. It is very good at finding massive planets that orbit close to their star, because these hot Jupiters cause the largest and fastest wobbles, making them easier to detect. The first planet found around a Sun-like star, 51 Pegasi b, was exactly this type of planet. A major advantage of this method is that it does not require the precise orbital alignment needed for the transit method. It can detect planets in a wide range of orbital inclinations. However, it is most sensitive to edge-on systems and becomes less sensitive as the orbit becomes more face-on. If a planet's orbit is perfectly face-on, there will be no motion towards or away from us, and the planet will be completely undetectable by this method. Another challenge is that it is very difficult to detect smaller, less massive planets, like Earth. The wobble caused by an Earth-sized planet on a Sun-like star is incredibly small, only about 9 centimeters per second. This is a very slow walking pace. Measuring such a tiny change in a star's velocity from trillions of kilometers away is an extraordinary technological feat, pushing the limits of our current instruments. An exciting aspect is when we can use both the transit method and the radial velocity method to study the same planet. This is the ultimate combination. The transit method gives us the planet's radius or its size. The radial velocity method gives us the planet's mass. And if you know both the mass and the radius of an object, you can calculate its density. Density is a crucial piece of information. It is mass divided by volume. Knowing a planet's density is the first and most important clue to understanding what it is made of. For example, if we find a planet with a low density, similar to Saturn's, we can be pretty sure it is a gas giant, made mostly of hydrogen and helium. If we find a planet with a high density, similar to Earth's, we can infer that it is a rocky planet, made of rock and metal. This combination of methods allows us to move beyond simply detecting planets to actually characterizing them and beginning to understand their composition, making them real worlds instead of just points on a graph. Now, let us briefly discuss a few other methods that are used to find exoplanets, although they have not discovered as many planets as the first two. One of these methods is called direct imaging. As the name suggests, this method involves taking an actual picture of the exoplanet itself. This is incredibly difficult for the reasons we discussed earlier. The star is incredibly bright, and the planet is incredibly faint and very close to the star. To make this possible, astronomers use special instruments called coronagraphs. A coronagraph is essentially a small, carefully placed mask inside the telescope that blocks out the direct light from the star. By blocking the starlight, it becomes possible to see the much fainter light of a planet orbiting nearby. This is still a very challenging technique. It works best for planets that are very large, like gas giants, and that are in very wide orbits, far away from their parent star. These planets are easier to separate from the star's glare. The planets also need to be young. Young planets are still hot from their formation, and they glow brightly in infrared light, which makes them easier to detect than older, colder planets that only reflect starlight. So far, only a few dozen exoplanets have been discovered through direct imaging, but the images we have obtained, even though they are often just small dots of light, are incredibly compelling. They provide direct, visual confirmation of these other worlds and allow us to study the light from the planet itself, which can tell us about its atmosphere. Another fascinating method is called gravitational microlensing. This method is based on Albert Einstein's theory of general relativity, which tells us that massive objects can bend the fabric of space-time. This bending of space-time can act like a lens. If a star with a planet passes directly in front of a much more distant background star from our point of view, the gravity of the foreground star will bend and magnify the light from the background star. As the foreground star drifts across the sky, it will cause the background star to appear to brighten and then fade in a very specific, predictable way. This event is called a gravitational lensing event. Now, if the foreground star also has a planet orbiting it, the planet's own gravity can add an extra little bit of lensing. This will cause a brief, extra spike of brightness on top of the main brightening event from the star. By looking for this short, sharp planetary signature in a lensing event, astronomers can deduce the presence of a planet around the foreground star. The microlensing method is unique because it is most sensitive to planets that are at a great distance from their star, in orbits similar to Jupiter's or Saturn's in our own solar system. This is a region of planetary systems that is difficult to probe with the transit or radial velocity methods. Microlensing is also capable of detecting very low mass, Earth-like planets, and even free-floating rogue planets that do not orbit any star at all. The major drawback of this method is that the alignment required for a microlensing event to occur is extremely rare and happens only once. We cannot go back and observe the planet again. It is a one-time event. So, while it gives us a valuable statistical snapshot of planets at large distances, it does not allow for follow-up studies of the planets it finds. There are other methods as well, such as astrometry, which tries to detect the tiny side-to-side motion of a star on the sky as it wobbles, and timing variations, which looks for tiny changes in the timing of signals from objects like pulsars or transiting planets, which can indicate the gravitational pull of another planet in the system. Each method has its own strengths and its own biases. The transit method is biased towards finding large planets in close-in orbits. The radial velocity method is biased towards finding massive planets in close-in orbits. Direct imaging is biased towards finding large, young planets in very wide orbits, and microlensing is biased towards finding planets at large distances. By using all of these different techniques, we can start to build up a more complete and less biased picture of the full population of planets that exists in our galaxy. Each method opens a different window onto the vast and diverse landscape of other worlds. The development of these ingenious techniques has transformed exoplanets from a subject of science fiction into a real and vibrant field of modern astronomy, providing us with thousands of new worlds to study and explore. Part 6. Common types of exoplanets, super-Earths, and hot Jupiters. Having explored the clever methods astronomers use to find planets orbiting other stars, we can now turn our attention to the planets themselves. What have we found? When we began discovering exoplanets, many people expected that we would find other solar systems that looked more or less like our own, with small, rocky planets close to the star and large gas giants farther out. But what we have discovered is a universe filled with a surprising and wonderful variety of planetary systems, many of which are very different from ours. We have found planets that are unlike anything we have in our own solar system. This has forced us to expand our ideas about how planets form and evolve. In this part of the lecture, we will explore some of the most common and significant types of exoplanets that have been discovered so far. We will focus on two particular classes of planets that have been found in great numbers and have challenged our understanding of planet formation. These are the hot Jupiters and the super-Earths. These two types of planets are not present in our solar system, but they appear to be very common throughout the galaxy. By studying them, we can learn about the different ways planetary systems can be built. Let's begin with the very first type of exoplanet to be discovered around a sun-like star, the hot Jupiter. The name itself gives you a very good idea of what these planets are like. They are Jupiters because they are giant planets with a mass similar to or even greater than our own Jupiter. They are gas giants composed primarily of hydrogen and helium. And they are hot because they orbit extremely close to their parent stars, much closer than Mercury orbits our Sun. The first such planet, 51 Pegasi b, was a complete shock to the astronomical community when it was discovered in 1995. It is a gas giant with about half the mass of Jupiter, but its orbit is incredibly small. It whips around its star in just over 4 Earth days. This means its orbital distance is only about 1/20th of the distance between the Earth and the Sun. Because it is so close to its star, its surface temperature is estimated to be over 1,000 degrees Celsius. This was a truly bizarre discovery. According to our theories of planet formation, which were based on our own solar system, a giant gas planet like Jupiter simply cannot form that close to a star. Let's think about why this is. Giant planets are thought to form in the cold, outer regions of a protoplanetary disk, the spinning disk of gas and dust that surrounds a young star. They need to form far from the star, beyond what is called the frost line or snow line. The frost line is the distance from the star where it is cold enough for volatile compounds like water, ammonia, and methane to condense into solid ice particles. These ice particles are very abundant in the outer disk. They can stick together and quickly build up a large core, about 10 times the mass of the Earth. Once a core gets this massive, its gravity is strong enough to start pulling in huge amounts of the surrounding hydrogen and helium gas from the disk. This is how a gas giant is born, closer to the star inside the frost line. It is too hot for these ices to form. Only rock and metal can exist as solids. There is much less of this solid material available, which is why the inner planets in our solar system, like Earth, are small and rocky. So, the discovery of a Jupiter-like planet in a Mercury-like orbit presented a major puzzle. It couldn't have formed where we see it today. This puzzle led to a new and important idea in planetary science, the concept of planetary migration. The idea is that hot Jupiters do not form in their current hot orbits. They form in the cold outer part of the planetary system, beyond the frost line, just as our theories predict. But then, after they have formed, something causes them to move. They migrate inwards, spiraling towards their star, until they eventually settle into the very close, stable orbits where we find them today. There are several theories about what could cause this migration. One of the leading ideas involves the protoplanetary disk itself. In the early days of a planetary system, the disk of gas and dust is still very thick. As a newly formed giant planet moves through this disk, it creates spiral waves in the gas, much like the wake of a boat moving through water. The gravity of these waves then pulls back on the planet. This interaction between the planet and the disk can cause the planet to lose orbital energy and spiral slowly inwards towards the star. This process, called disk migration, would continue until the planet gets very close to the star, where the disk has been cleared out, or until the gas in the disk dissipates completely. At that point, the migration would stop, leaving the planet stranded in a very tight orbit. Another theory for how a hot Jupiter might end up in its close orbit involves gravitational interactions with other planets in the system. This is sometimes called planet-planet scattering. In this scenario, a newly formed planetary system might be unstable. The gravitational pulls of multiple giant planets on each other could cause their orbits to become chaotic. Over time, these gravitational encounters could fling one of the planets into a very eccentric or elliptical orbit that takes it very close to the star. Then, over a long period, tidal forces between the planet and the star would circularize the orbit, shrinking it down into the tight, circular path of a hot Jupiter. This process might also explain why many hot Jupiter systems seem to have only one giant planet, as any other planets may have been ejected from the system entirely during the chaotic scattering phase. It is likely that both of these mechanisms, disk migration and planet-planet scattering, play a role in creating the hot Jupiters we see. Because hot Jupiters are so close to their stars, they are subject to extreme conditions. The intense radiation from the star heats their atmospheres to very high temperatures. This causes the planet's atmosphere to expand and puff up. As a result, many hot Jupiters have a very large radius for their mass, making them even less dense than our own Jupiter or Saturn. They are sometimes called puffy planets or hot Saturns. The side of the planet that permanently faces the star can be incredibly hot, while the side that faces away into space, the night side, can be significantly cooler. This large temperature difference can drive incredibly powerful winds with speeds of thousands of kilometers per hour that blow from the hot day side to the cooler night side, trying to even out the temperature. The intense stellar radiation can also strip away the planet's atmosphere over time. This process is called atmospheric escape or photoevaporation. The high-energy ultraviolet and X-ray radiation from the star heats the upper layers of the planet's atmosphere, giving the gas particles enough energy to escape the planet's gravity and fly off into space. Some hot Jupiters have been observed to have huge, comet-like tails of escaping gas trailing behind them over billions of years. This process could potentially strip a gas giant of its entire atmosphere, leaving behind only its solid core. We will talk more about these hypothetical remnants, called chthonian planets, in the next part. Because they are large and orbit so close to their stars, hot Jupiters produce very strong signals for both the transit method and the radial velocity method. They block a lot of starlight during a transit, and the transits happen very frequently, making them easy to spot. They also cause a very large and rapid wobble in their parent star. This is why hot Jupiters were the first type of exoplanet to be found in large numbers. They are, in a sense, the low-hanging fruit of exoplanet detection. For a long time, it seemed like they might be the most common type of giant planet in the galaxy. However, we now know that this is a selection effect. They are easy to find, so we find a lot of them. More recent studies suggest that they are actually quite rare, existing around only about 1% of sun-like stars. Cooler giant planets, like our own Jupiter, are likely much more common, but they are harder to detect because their orbits are much longer. Now, let us turn to the second and arguably more significant category of exoplanets. These are the super-Earths. The term super-Earth refers to a planet that has a mass greater than Earth's, but substantially less than the masses of our solar system's ice giants, Uranus and Neptune. The mass range for a super-Earth is typically defined as being between 1 and 10 times the mass of the Earth. Their radii are usually between 1 1.25, and 2 times the radius of Earth. The most astonishing thing about super-Earths is that they are incredibly common. Data from the Kepler mission has shown that super-Earths are one of the most abundant types of planets in the galaxy. They appear to orbit at least 30 to 40% of Sun-like stars. This is a remarkable finding because our own solar system does not have a single planet in this size and mass range. The largest terrestrial planet in our solar system is Earth. The smallest giant planet is Neptune, which is about 17 times the mass of Earth. There is a huge gap in between. We have no in-between planets, but the universe, it seems, loves to make them. The fact that our solar system lacks the most common type of planet is a fascinating puzzle and a lesson in how our local environment may not be representative of the galaxy as a whole. The term super-Earth can be a bit misleading. It does not necessarily mean that these planets are like a scaled-up version of Earth, with continents, oceans, and life. The name only refers to the planet's mass. The nature of a super-Earth depends heavily on its density, which tells us what it is made of. The category of super-Earths actually includes a wide variety of different types of planets. Some super-Earths are likely to be true terrestrial or rocky planets, just bigger versions of Earth or Mars. If a super-Earth has a high density, similar to Earth's, we can infer that it is made mostly of rock and metal, with a solid surface. A more massive, rocky planet could have different geological properties than Earth. Its stronger gravity could lead to a flatter topography, with no high mountains or deep ocean trenches. Its stronger gravity would also allow it to hold on to a much thicker atmosphere. Plate tectonics, the process that shapes Earth's surface, might operate differently, or not at all, on such a massive world. Some of these rocky super-Earths could potentially be habitable if they orbit within their star's habitable zone, the region where liquid water could exist on the surface. A super-Earth in the habitable zone might even be a super-habitable world, with conditions even more stable and conducive to life than Earth's. However, not all super-Earths are rocky. Many of the planets in the super-Earth size range seem to have a much lower density. This suggests that they are not purely rocky. These low-density super-Earths are likely planets that have a substantial envelope of gas around them, primarily hydrogen and helium. These planets are often called mini-Neptunes, or gas dwarfs. They represent a transition point between the rocky terrestrial planets and the large ice or gas giants. A mini-Neptune would not have a solid surface. It would have a rocky core at its center, surrounded by a very thick, dense atmosphere. As you descend into a mini-Neptune, the pressure would increase until the atmosphere becomes a strange, hot fluid. These worlds would be completely inhospitable. There appears to be a dividing line between the rocky super-Earths and the gaseous mini-Neptunes. Studies of the thousands of planets found by Kepler have revealed a fascinating feature in the distribution of planet sizes. It turns out that there are very few planets with a radius of about 1.5 to 2 times the radius of Earth. Planets tend to be either smaller than 1.5 times Earth's radius or larger than 2 times Earth's radius, with a gap in between. This feature is known as the radius valley or the Fulton Gap. The existence of this radius valley is thought to mark the transition between rocky planets and gaseous planets. Planets smaller than about 1.5 times Earth's radius are likely to be the true rocky super-Earths. They are dense enough that their gravity can hold onto them, but they are not massive enough to have captured a large amount of hydrogen and helium gas from the protoplanetary disk when they formed. Planets larger than about 2 times Earth's radius are likely the mini-Neptunes. They formed with a large enough core that they were able to accrete a thick atmosphere of light gases. The radius valley itself might be created by the process of photoevaporation, the same process that can strip the atmospheres of hot Jupiters. Planets that form with a thin gaseous envelope might have that atmosphere completely stripped away by the radiation from their star, leaving behind only the bare, rocky core. This would shrink their radius and move them into the rocky super-Earth category. Planets that form with a much thicker, more massive atmosphere would be able to hold on to it, remaining as mini-Neptunes. The planets that would fall into the radius valley are those that are just right to lose their atmospheres, creating a gap in the population. Another fascinating possibility for some super-Earths is that they could be ocean worlds or water worlds. A super-Earth that formed far from its star, beyond the frost line, could have been composed of a very large fraction of water ice, perhaps as much as 50% of its mass. If this planet then migrated inwards to a warmer region of the solar system, that vast amount of ice would melt, creating a planet with no dry land at all, just a single global ocean, hundreds or even thousands of kilometers deep. Beneath this immense ocean would be a layer of exotic, high-pressure forms of ice, and at the very center, a rocky core. While the idea of a world covered in water sounds appealing, such a planet might not be very hospitable for life as we know it. The deep ocean would prevent the cycling of minerals from the rocky core to the water, which is thought to be an important process for sustaining life on Earth. The discovery of the sheer abundance of super-Earths and mini-Neptunes has fundamentally changed our perspective. It shows that our solar system's architecture, with its clear separation between small rocky planets and giant gas planets, is just one possible outcome of planet formation. The universe seems to have no problem making planets of intermediate size. The question of why our solar system lacks a super-Earth is a very active area of research. One theory suggests that the presence of our giant planet, Jupiter, may have prevented a super-Earth from forming. Jupiter's powerful gravity may have disrupted the region of the inner solar system, either by flinging the building blocks of a potential super-Earth out of the system, or by gobbling them up itself during its own formation and possible early migration. In this view, our solar system might be unusual, not because of what it has, but because of what it is missing. So, hot Jupiters and super-Earths represent 2 major classes of exoplanets that have been found in large numbers. Hot Jupiters are gas giants in scorching close-in orbits, and their existence has taught us about the importance of planetary migration. Super-Earths are planets larger than Earth, but smaller than Neptune, and their incredible abundance tells us that our solar system's architecture is not the only or even the most common design. The category of super-Earths itself contains a diverse range of worlds, from large rocky planets to gaseous mini-Neptunes to potential water worlds. These are not the only types of exoplanets. Of course, we have also found many planets that are more familiar. We have found cold Jupiters, which are gas giants in wide, long-period orbits, much like our own Jupiter and Saturn. These are harder to detect, but they are likely very common. We have also found many Earth-sized and Mars-sized planets, which fall into the category of terrestrial planets. Finding these smaller planets is very challenging, but missions like Kepler have succeeded in discovering hundreds of them. Some of these rocky, Earth-sized worlds have been found orbiting within the habitable zones of their stars, making them prime targets in the search for life beyond Earth. The study of exoplanets has revealed a zoo of different worlds. We have found planets orbiting binary star systems, like the fictional planet Tatooine from Star Wars. We have found planetary systems that are incredibly compact, with multiple planets orbiting much closer to their star than Mercury orbits our Sun. We have found planets with highly eccentric, comet-like orbits. We have found systems where the planets orbit in the opposite direction to their star's spin. The diversity is staggering. Each new discovery adds another piece to the puzzle of how planets form and how solar systems evolve. The picture that is emerging is one of incredible richness and variety. Our solar system is just one example among billions, a single, familiar melody in a vast and complex cosmic symphony. The common types of planets we have discussed, the hot Jupiters and the ubiquitous super-Earths, are some of the dominant chords in that symphony, reminding us that the universe is far more imaginative and varied than we ever thought possible. Part 7. Exotic and extreme planetary types. In our journey so far, we have covered the planets of our own solar system and some of the most common types of exoplanets discovered to date, such as the surprising hot Jupiters and the incredibly abundant super-Earths. These discoveries have already shown us that the universe is capable of building worlds in ways we had not anticipated. But the diversity of planets does not stop there. As our methods of detection become more sensitive and our theoretical models become more sophisticated, we are beginning to uncover and imagine planets that are even more strange, more extreme, and more exotic. In this part of our lecture, we will venture into the wilder side of planetary science. We will explore some of the more unusual types of planets that are thought to exist, some of which have observational evidence to support them, and some of which remain, for now, in the realm of theory. These are the planets that push the boundaries of what we thought was possible. We will discuss the scorched, naked cores of giant planets, worlds made of diamond, planets completely covered in a global ocean, worlds locked in a permanent stare with their star, and planets that wander alone through the dark emptiness of space. These exotic worlds may be rare, but studying them helps us to understand the full range of possibilities for planetary formation and evolution under all kinds of different conditions. Let us begin with a type of planet that is a direct consequence of the extreme environment experienced by some hot Jupiters. This is the hypothetical world known as a chthonian planet. The name comes from the Greek word for of the earth, or underworld, and it refers to the bare, rocky core of a gas giant that has been left behind after its atmosphere has been completely stripped away. We discussed earlier how hot Jupiters, being so close to their parent stars, are subjected to intense radiation. This radiation can heat up the planet's atmosphere and cause it to escape into space over billions of years, a process called photoevaporation. If a gas giant or an ice giant migrates very close to its star, this process could be so extreme that the entire massive envelope of hydrogen and helium, or the mantle of water, ammonia, and methane, is boiled away. what would be left behind? The only thing that would remain is the dense, solid core that was once at the very center of the giant planet. This naked core, now orbiting its star alone, is what we call a Chthonian planet. A Chthonian planet would be a truly hellish world. It would be a terrestrial planet, in the sense that it is rocky and has a solid surface, but it would be unlike any terrestrial planet in our solar system. It would be much more massive and much denser than Earth. It would be orbiting its star at an incredibly close distance, resulting in surface temperatures of thousands of degrees Celsius, hot enough to melt rock. The surface would likely be a molten ocean of lava. It would be a world constantly blasted by the fierce radiation and stellar wind of its nearby star. Have we found any of these Chthonian planets? Finding a confirmed example is very difficult, but there are some intriguing candidates. One of the most famous is a planet called Corot 7b. This was one of the first rocky exoplanets to be discovered. It is a super-Earth with a mass about 5 times that of Earth, but it orbits its star in less than 1 day. Its orbital period is only about 20 hours. This means it is incredibly close to its star, and its surface temperature is estimated to be over 2,000 degrees Celsius. Because of its mass and its extreme orbit, some astronomers have suggested that Corot 7b might not have formed as a rocky planet. Instead, it might be the remnant core of a gas giant that had its atmosphere stripped away. Another candidate is a planet designated HD 219134b, a nearby super-Earth that is also very dense and orbits its star in just 3 days. These planets fit the profile of what we would expect a Chthonian planet to look like. They are very dense, rocky worlds in scorching hot orbits. While we cannot be certain that they are the remains of former giants, they represent a fascinating possibility and show how planets can be transformed by their environments. Now, let's move on to another type of theoretical planet, one that is based on chemistry rather than just heat and gravity. This is the concept of a carbon planet, sometimes called a diamond planet. All of the terrestrial planets in our solar system, like Earth and Mars, are silicate-based. This means that their crust and mantle are made primarily of rocks based on silicon and oxygen. This is because in the part of the solar nebula where Earth formed, oxygen was more abundant than carbon. But what if a planet formed in a region of a protoplanetary disk where there was more carbon than oxygen? In such a carbon-rich environment, the chemistry of planet formation would be completely different. The planet that would form would not be a silicate world. It would be a carbon planet. In a carbon-rich, oxygen-poor environment, the available carbon would combine with metals to form carbides, like silicon carbide, instead of silicates. The planet's core would still likely be made of iron, just like Earth's, but the mantle above it would be made of carbon-based compounds. Deeper inside the mantle, where the pressure is immense, the carbon could be squeezed into its most famous and durable form, diamond. So, a carbon planet could theoretically have a thick layer in its interior that is made of pure diamond, potentially thousands of kilometers thick. The surface of such a planet would be a strange and dark place. It would likely be covered in a layer of graphite, which is another form of carbon. There could be pools or oceans not of water, but of liquid hydrocarbons like tar or oil. The atmosphere of a carbon planet, if it had one, would be rich in carbon monoxide and methane, with very little oxygen or water vapor. There would be no water on a carbon planet. as any oxygen would be locked up in carbon monoxide. It would be a world of black graphite plains, diamond mountains, and oily seas, under a smoggy, yellow-brown sky. Is there any evidence for such worlds? The evidence is tentative, but there are some hints. The first potential candidate was a planet found orbiting a pulsar, named PSR JA1719-38b. This object is extremely dense for its size, which led some to speculate that it could be a planet made of crystalline carbon or diamond. Another, more famous candidate was an exoplanet called 55 Cancri e. This is a super-Earth, orbiting a star that is known to be very rich in carbon. Early measurements of the planet's mass and radius suggested it had a very high density, consistent with a carbon-rich composition. The idea that 55 Cancri e could be a diamond planet captured the public imagination. However, more recent and precise measurements have revised its density downwards, and it is now thought to be more likely a very hot, rocky planet with a thick atmosphere, or perhaps a world with a large amount of water in a supercritical state. So, while the existence of a true diamond planet has not yet been confirmed, the possibility remains. The chemistry of the star and its protoplanetary disk should have a direct influence on the composition of the planets that form, and it is plausible that in some carbon-rich systems, these exotic carbon worlds could exist. Next, let's consider another type of world that is defined by its surface composition, the ocean world or water world. We touched on this idea when we discussed super-Earths, but let's explore it in more detail. An ocean world is a planet that is completely, or almost completely, covered by a single global ocean of liquid water. These are not planets like Earth, which has both continents and oceans. These are planets with no exposed land at all. Such a world could form in a couple of ways. A planet that forms in the outer, colder regions of a solar system beyond the frost line would incorporate a huge amount of water ice into its composition. If this icy planet then migrates inwards to the habitable zone, where the temperature is right for liquid water, all of that ice would melt. If the planet had a large enough water content, say 25% or more of its total mass, the resulting ocean would be incredibly deep, potentially hundreds of kilometers deep. This is far deeper than any ocean on Earth, which has an average depth of only about 4 kilometers. Life on such a world would face very different conditions than on Earth. On the one hand, a global ocean would provide a very stable environment. The vast amount of water would regulate the planet's temperature, preventing extreme swings between hot and cold. But life might struggle to get started and to sustain itself. On Earth, the interaction between the oceans and the continents is thought to be very important. Runoff from the land provides essential nutrients, like phosphorus, to the oceans. Hydrothermal vents on the ocean floor, where tectonic plates meet, also release minerals and chemical energy. On a deep ocean world, the water would be separated from the rocky mantle below by a thick layer of high-pressure ice. As you go deeper into the ocean, the pressure would become so great that it would compress the water into a solid, even if it is still warm. This layer of ice, called ice V6 or ice 7th, would form a barrier between the ocean and the rocky core, preventing the cycling of nutrients. Life might be confined to the upper layers of the ocean, with a very limited supply of the chemical building blocks it needs. We have not yet confirmed the existence of a true ocean world, but there are some good candidates. The planets in the TRAPPIST-1 system, a nearby system, with 7 Earth-sized planets, are thought to have a significant amount of water. Some of them, depending on their exact composition and temperature, could be ocean worlds. Another candidate is a planet called Kepler 22b, a super-Earth orbiting in the habitable zone of a sun-like star. Its size and orbit are consistent with it being a warm ocean world. Future telescopes, like the James Webb Space Telescope, will be able to study the atmospheres of these planets. By looking for large amounts of water vapor, they might be able to tell us if these worlds are indeed covered in planet-spanning oceans. Now, let's think about a type of planet defined not by its composition, but by its relationship with its star. This is the eyeball planet. An eyeball planet is a world that is tidally locked to its star. Tidal locking is a situation where a planet's rotation period is exactly the same as its orbital period. The result is that the planet always shows the same face to its star, just as our moon always shows the same face to the Earth. This means one side of the planet is in permanent, unending daylight, while the other side is in permanent, unending darkness. Tidal locking is very common for planets that orbit close to their star, especially for planets orbiting small, cool stars called red dwarfs. Red dwarfs are the most common type of star in the galaxy, and many planets have been found orbiting them in their habitable zones. But because red dwarfs are so cool, their habitable zone is very close to the star. Any planet in the habitable zone of a red dwarf is almost certain to be tidally locked. What would such a world be like? It would be a planet of 2 extremes. The side facing the star, the day side, would be constantly baked by the star's radiation and could become very hot, possibly hot enough to boil away any water. The side facing away from the star, the night side, would receive no sunlight at all and would be incredibly cold, likely covered in a thick sheet of ice. The hope for habitability on such a world lies in the region between these 2 extremes. This is the terminator, or the twilight zone, the narrow ring around the planet where day and night meet. In this twilight zone, the temperature might be just right for liquid water to exist. A strong atmosphere could also help to even out the temperatures by transporting heat from the hot day side to the cold night side with powerful winds. The appearance of such a planet from a distance would be striking. If the planet has an ocean, the day side might have a large, circular patch of open water where the starlight is strongest, surrounded by a ring of ice. This would make the planet look like a giant eyeball staring out into space, with the patch of water as its pupil. This is where the name eyeball planet comes from. There could be different types of eyeball planets. A hot eyeball would have a dry, baked day side and liquid water only on the night side. A cold eyeball, or icy eyeball, would be mostly frozen with a sea or lake of melted water only at the substellar point, the spot on the day side directly beneath the star. The planets of the TRAPPIST-1 system are all likely to be tidally locked, and so they could be examples of eyeball planets. The question of whether these strange worlds could support life is one of the most exciting topics in astrobiology today. Finally, let us consider the loneliest planets of all, rogue planets. These are also known as free-floating planets, interstellar planets, or orphan planets. A rogue planet is a planet that does not orbit a star. It has been ejected from the planetary system where it formed and now wanders through the vast, cold darkness of interstellar space on its own. How could a planet become a rogue? The most likely mechanism is the same kind of chaotic gravitational interaction that can create hot Jupiters. In the early, unstable days of a planetary system, close gravitational encounters between giant planets can act like a slingshot. One planet might be flung inwards, while another planet is flung outwards with so much energy that it completely escapes the star's gravitational pull. It is then cast out into the galaxy to travel alone. This process could be quite common. Some estimates suggest that there could be as many or even more rogue planets in our galaxy as there are stars. A rogue planet would be a very dark and cold place. With no star to warm it, its surface temperature would drop to just a few degrees above absolute zero. Any atmosphere it had would freeze and snow down onto the surface. It would be a world encased in ice, drifting silently through the void. Could such a world possibly support life? It seems almost impossible, but there are some speculative ideas. If a rogue planet is large enough, a gas giant like Jupiter, it could still have a source of heat from its own interior, a remnant of its formation. This internal heat might not be enough to warm the surface, but it could potentially keep a liquid water ocean warm under a thick surface layer of ice. Life could potentially exist in this subsurface ocean, feeding on chemical energy, much like the life we imagine might exist in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. Such a rogue planet would need to have a very thick atmosphere of hydrogen to act as an insulating blanket to trap its internal heat. Finding these rogue planets is extremely difficult. They do not shine, and they are not near a star, so we cannot use the transit or radial velocity methods. The most promising way to find them is through gravitational microlensing. As we discussed, if a massive object passes in front of a distant star, it can magnify the star's light. A rogue planet, being a massive object, can do this as well. When a rogue planet passes in front of a background star, it will cause a brief, characteristic brightening. The duration of this brightening event tells us about the mass of the lensing object. Very short duration events, lasting for a few hours or a couple of days, are a strong sign that the object is a planet mass object, not a star. Several such short duration microlensing events have been detected, providing the first tentative evidence for this vast, hidden population of wandering worlds. These exotic and extreme planets, from the fiery cores of Chthonian planets to the dark and lonely rogue planets, stretch our imagination and challenge our definitions. They show us that the processes of planet formation can lead to an incredible variety of outcomes, far beyond what we see in our own familiar solar system. They remind us that the universe is a place of endless possibilities, with strange and wonderful worlds waiting to be discovered in every corner of the galaxy. Each one is a piece of the puzzle, helping us to build a more complete picture of how planets, and perhaps even life, can exist in the cosmos. Part 8. The Habitable Zone and the Search for Life. In this final part of our lecture, we will bring together all the different threads we have been discussing. We have explored the definition of a planet. We have toured the diverse worlds of our own solar system, and we have journeyed into the vast and varied zoo of exoplanets orbiting distant stars. Now, we will focus on the question that lies at the heart of all this exploration, the question that drives so much of our interest in other worlds. That question is, are we alone in the universe? Is Earth the only planet that harbors life, or could life exist on some of the other planets we have discovered. This is one of the oldest and most profound questions that humanity has ever asked. For most of history, it has been a question for philosophers and storytellers. But today, for the first time, it is becoming a question that we can begin to answer with science. The search for life beyond Earth, a field known as astrobiology, is now a major focus of modern astronomy. Scientists are actively looking for planets that might have the right conditions for life and for signs of life itself. To begin this search, we need a starting point. The universe is a vast place, and we cannot examine every planet. We need a way to narrow down the search to the most promising candidates. The primary tool that scientists use for this is a concept known as the habitable zone. The habitable zone is a simple but powerful idea that helps us identify which planets are the best places to look for life as we know it. So, what is the habitable zone? The habitable zone is defined as the region around a star where the conditions are just right for a planet to have liquid water on its surface. It is the orbital range where a planet is not too hot and not too cold, but just right. This is why it is often nicknamed the Goldilocks zone. If a planet is too close to its star, it will be too hot. Any water on its surface would boil away into steam, like on Venus. If a planet is too far from its star, it will be too cold. Any water on its surface would freeze into solid ice, like on Mars today, or on the moons of the outer solar system. But in the habitable zone, the temperature is moderate enough that water can exist in its liquid form. Why is liquid water so important? The search for life beyond Earth is, for now, a search for life as we know it, and all life on Earth, from the smallest bacterium to the largest blue whale, depends on liquid water. Water is a fantastic solvent, meaning it can dissolve many other substances. This allows it to transport the chemicals that are necessary for the reactions of life to occur inside cells. Water also plays a crucial role in regulating temperature and in many other biological processes. It is so fundamental to life on Earth that it is hard to imagine life getting started or surviving without it. So, when we look for life elsewhere, the first and most logical step is to look for water, and the easiest place to find liquid water is on the surface of a planet. That is why the habitable zone is defined by the potential for liquid surface water. The size and location of the habitable zone are not the same for every star. It depends entirely on the type of star. A star's type is determined by its mass, which in turn determines its temperature and its brightness. Let's consider a star like our Sun, which is a G-type star. For our Sun, the habitable zone is roughly located between the orbits of Venus and Mars. Earth, of course, sits comfortably right in the middle of this zone. Now, let's think about a star that is much hotter and brighter than our Sun, like a large A-type or F-type star. Because this star is putting out much more energy, its habitable zone will be located much farther away from the star. A planet would need to be in a wider orbit to have the same moderate temperature as Earth. The habitable zone would also be wider. However, these large, hot stars have a major drawback. They burn through their fuel very quickly. A star like our Sun will live for about 10 billion years, which has given life on Earth plenty of time to evolve. A massive star might only live for a few 100 million years, or even less. This may not be enough time for complex life to get started and evolve. Now, let's consider the opposite case. a star that is much smaller, cooler, and dimmer than our Sun. These are the M-type stars, also known as red dwarfs. As we have mentioned, red dwarfs are the most common type of star in our galaxy, making up about 75% of all stars. Because these stars are so cool and faint, their habitable zone is located very, very close to the star. A planet would need to be in a very tight orbit, much closer than Mercury is to our Sun, in order to be warm enough for liquid water. The habitable zone around a red dwarf is also much narrower than the zone around a Sun-like star. Red dwarf stars have a very long lifespan, trillions of years, which would seem to give life plenty of time to evolve. This makes them very interesting targets in the search for life. In fact, some of the most famous, potentially habitable exoplanets we have found, like those in the TRAPPIST-1 system and our nearest neighbor, Proxima Centauri b, orbit red dwarf stars. However, planets orbiting in the habitable zone of a red dwarf would face some significant challenges. As we discussed in the previous part, a planet that is very close to its star is likely to become tidally locked. This would create a world with a permanent hot day side and a permanent cold night side, a so-called eyeball planet. Whether such a world could be truly habitable is still a topic of debate. Another major problem with red dwarfs is that they can be very active stars, especially when they are young. They can produce powerful stellar flares, which are sudden, intense bursts of radiation. A planet orbiting very close to the star would be blasted by these flares, which could strip away its atmosphere and bathe its surface in deadly radiation, making it very difficult for life to survive. So, the concept of the habitable zone is our first pass filter. When we discover a new exoplanet, one of the first things we do is to calculate its orbit and see if it falls within its star's habitable zone. If it does, it becomes a planet of high interest, a potentially habitable world. We have now discovered dozens of exoplanets that are roughly Earth-sized and that orbit within the habitable zone of their star. These are the most exciting targets we have in the search for alien life. However, it is extremely important to understand that being in the habitable zone does not guarantee that a planet is habitable. It only means that the planet has the potential for liquid water on its surface. It is a necessary condition, but it is not a sufficient condition. Many other factors must also be right for a planet to be a truly good home for life. One of the most important of these factors is the planet's atmosphere. A planet needs to have a substantial atmosphere to be habitable. An atmosphere does several crucial things. First, it provides the surface pressure needed for liquid water to be stable. If the atmospheric pressure is too low, water will just boil away into space, even if the temperature is right. This is what happens on Mars today. Second, an atmosphere provides protection. It shields the surface from harmful high-energy radiation from the star, like ultraviolet rays and X-rays, and from cosmic rays from deep space. A layer of ozone, like the one we have on Earth, is particularly important for blocking UV radiation. Third, an atmosphere helps to regulate the planet's temperature through the greenhouse effect. The greenhouse effect is often talked about as a negative thing, but a moderate amount of it is essential for life. Without the greenhouse gases in our atmosphere, like carbon dioxide and water vapor, the average temperature of the Earth would be about -18 degrees Celsius, and the planet would be a frozen ice ball. A planet in the habitable zone needs to have the right kind of atmosphere with the right amount of greenhouse gases to maintain a stable, moderate temperature. The size of the planet is also critical. A planet needs to be large enough to have enough gravity to hold onto its atmosphere over billions of years. A small planet, like Mars, has weak gravity. Over time, it can lose most of its atmosphere to space, especially if it doesn't have a protective magnetic field. This is what we think happened to Mars. It was once warmer and wetter, with a thicker atmosphere, but it lost most of it over time, turning it into the cold, dry desert we see today. A planet also needs to be large enough to remain geologically active for a long time. Geological activity, like volcanism and plate tectonics, is important for regulating the climate over long timescales. The carbon cycle on Earth, for example, involves carbon dioxide being released by volcanoes and then removed from the atmosphere by rain and chemical reactions with rocks. This acts like a global thermostat, helping to keep the climate stable. This geological activity is powered by heat from the planet's interior. A smaller planet will cool down faster, and its geological activity will cease. So, a planet needs to be in a certain size range, not too small and not too large, to be considered truly Earth-like and potentially habitable. The presence of a magnetic field is another very important factor. A strong global magnetic field, like Earth's, is generated by a liquid rotating core. This magnetic field creates a protective bubble around the planet, the magnetosphere, which deflects the solar wind. The solar wind is a constant stream of charged particles flowing out from the star. Without a magnetic field, the solar wind can directly impact the planet's upper atmosphere and slowly strip it away. This is another reason why Mars lost its atmosphere. It lost its global magnetic field early in its history. So, a truly habitable planet is not just about being at the right distance from its star. It needs to have the right size, the right composition to allow for geological activity, a substantial atmosphere with the right properties, and a protective magnetic field. It is a long and complex checklist. This is why some scientists talk about the rare Earth hypothesis, the idea that while simple microbial life might be common in the universe, the specific combination of circumstances needed for a complex, animal and plant-filled world like Earth might be incredibly rare. Now, let's say we have found a promising candidate. We have found a rocky, Earth-sized planet orbiting in the habitable zone of a sun-like star. How can we take the next step? How can we actually look for signs of life on that distant world? We cannot travel there to collect samples. We have to do it from here, using our telescopes. The way we will search for life is by looking for something called a biosignature. A biosignature is any substance, object, or pattern whose origin specifically requires a biological process. In the context of exoplanets, we are primarily looking for atmospheric biosignatures. These are gases in a planet's atmosphere that are produced by living organisms and that would not normally be there in large quantities without life. By studying the chemical composition of an exoplanet's atmosphere, we might be able to see the fingerprint of a living biosphere. How do we study the atmosphere of a planet that is light years away? The primary method is called transmission spectroscopy, and it is a technique that can be used on transiting exoplanets. When a planet passes in front of its star, a small fraction of the starlight passes through the thin ring of the planet's atmosphere on its way to us. Different gases in the atmosphere will absorb light at specific colors or wavelengths by taking a spectrum of the starlight just before the transit, and then during the transit, we can see what colors of light have been absorbed by the atmosphere. This tells us which gases are present. This technique is incredibly challenging because the signal from the atmosphere is extremely small, but powerful new instruments, like the James Webb Space Telescope, are designed to do exactly this. So, what gases are we looking for? What are the key biosignatures? The most sought-after biosignature is oxygen. On Earth, the 21% of our atmosphere that is oxygen is almost entirely produced by photosynthesis, the process used by plants, algae, and some bacteria to convert sunlight, water, and carbon dioxide into energy. Without life constantly replenishing it, the oxygen in our atmosphere would quickly react with rocks and other chemicals and disappear. So finding a large amount of oxygen in the atmosphere of a rocky planet in the habitable zone would be an incredibly exciting discovery. It would be a very strong sign that some kind of photosynthesis-like process is occurring on that world. However, oxygen alone might not be a foolproof sign of life. There are some non-biological or abiotic processes that could potentially produce oxygen in a planet's atmosphere. For example, if a planet has a lot of water and is being hit by strong ultraviolet radiation from its star, the UV light could split the water molecules into hydrogen and oxygen. The light hydrogen gas could escape into space, leaving the heavier oxygen behind. This could build up an oxygen atmosphere without any life being present. To be more confident, scientists prefer to look for a combination of gases that are out of chemical equilibrium with each other. This means finding two or more gases in the same atmosphere that should not exist together, because they would normally react with each other and be destroyed. The only way to keep them both present in large quantities is if something like life is constantly producing both of them. The classic example of this on Earth is the combination of oxygen and methane. Methane is a gas that is produced by many living organisms on Earth, particularly by microbes called methanogens. Methane reacts with oxygen and is quickly destroyed. So, finding both a lot of oxygen and a lot of methane in the same atmosphere would be a very powerful biosignature. It would be very difficult to explain this combination with geology or chemistry alone. It would strongly suggest that there is a large, active biosphere on the planet, with some organisms producing oxygen and other organisms producing methane. There are other potential biosignatures as well. We could look for gases like nitrous oxide, which is produced by bacteria on Earth, or certain sulfur compounds. Scientists are also thinking about more general signs of life. For example, we could look for a lack of carbon monoxide. On a habitable planet with an ocean, carbon monoxide from volcanoes should be quickly consumed by microbes. So, a very low amount of it could be a sign of life. We could also look for seasonal changes in the atmospheric composition, as the activity of a biosphere might change with the seasons. The search for biosignatures is just beginning. With the launch and operation of the James Webb Space Telescope, we are entering a new era of exoplanet characterization. This powerful telescope has the sensitivity to study the atmospheres of some of the most promising nearby transiting exoplanets, like those in the TRAPPIST-1 system. It will search for water vapor, methane, carbon dioxide, and other gases. It might even be able to detect oxygen, although that will be very difficult. Over the next few years and decades, we will begin to get our first real data on the atmospheres of these potentially habitable worlds. It is important to manage our expectations. Finding a definitive, unambiguous sign of life will be a long and difficult process. The first hints are likely to be ambiguous. We might find a planet with some oxygen, but we will not be sure if it is from life or from an abiotic process. The scientific community will debate the results, and we will need to build even more powerful next-generation telescopes to make more detailed observations and confirm any findings. The discovery of extraterrestrial life will probably not be a single eureka moment. It will more likely be a slow, gradual process of accumulating evidence until we reach a point where we are confident that the best explanation for what we are seeing is the presence of life. But even with all these challenges, this is a uniquely exciting time to be alive. We have gone from knowing about only one planetary system to knowing about thousands. We have discovered a rich diversity of worlds, many of which are unlike anything we could have imagined. We have identified dozens of planets that have the potential to be habitable, and now we are taking the first concrete steps towards analyzing the atmospheres of these worlds and searching for the chemical fingerprints of life. We are on the verge of being able to answer that ancient, fundamental question: whether we find that life is common in the galaxy or that Earth is a rare and precious exception. The answer will be one of the most important discoveries in the history of science. It will forever change our perspective on the universe and on our own place within it. Our long lecture on the different types of planets has brought us here, to the very frontier of human knowledge, staring out at the countless points of light in the night sky and wondering, with real scientific purpose,